Your brain may not be a closed machine, it might be a quantum antenna tuned to the deepest fabric of reality. In the space between neurons, where physics turns strange, some scientists think awareness could be written into the universe itself. If consciousness is quantum, are your thoughts truly private, or are they entangled with everything that exists? There is a moment every day when the universe becomes personal, when raw physics turns into a point of view. We can map the circuitry, measure the signals, and still not locate the someone who is hearing this. In this film, we follow a question that refuses to stay in one discipline, because it begins in the most intimate place and ends at the edge of what science can currently say. Your experience arrives complete. Colour, pain, memory, meaning, and the quiet certainty that it is happening to you. Yet when we open the skull, we find only living tissue, chemical gradients, and electrical storms, magnificent machinery, but not an obvious doorway to a first-person world. Neuroscience has earned its confidence by explaining how perception is built, how attention selects, and how memory binds a life into a narrative. It can predict decisions in narrow tasks, watch moods shift with molecules, and trace the loops that keep you awake, dreaming, or gone. But correlation is not explanation. Decoding a pattern is not the same as finding the felt presence behind it. So we widen the frame with discipline, not with slogans, and we set ground rules that will not bend for wonder. We will separate consciousness from cognition, and private qualia from reportable access, because the words themselves can smuggle conclusions. We will treat split brains, anesthesia, seizures, and sleep as boundary tests, where awareness can fracture or vanish on schedule, and where any theory must answer to clinical reality. Then we take a hard look at the most successful theory in the history of physics, quantum mechanics. Not as a metaphor for mystery, but as a precise account of matter that builds atoms, chemistry, and every modern device you depend on. Here the world behaves in ways that defy common sense. Superposition, interference, entanglement, and a measurement problem that still divides experts even after a century. Only after that groundwork do we return to the brain, and we take it seriously on its own terms. We follow spikes and synapses, inhibition and synchrony, and the large-scale networks that may broadcast information into awareness. We watch how consciousness tracks brain state with unsettling reliability, and we ask what any proposal must explain if it hopes to be more than poetic. From there, we go deeper than neurons, into the scaffolding inside them, where microscopic structures guide transport and shape the cell's internal life. Some researchers see in this hidden architecture a candidate for physics beyond classical computation. Others see a biological system too warm, wet, and noisy for fragile quantum states. The tension is the point, and the details matter. At the center of our journey sits a controversial bridge between mind and physics, built from a specific proposal with specific claims. We will not grant it authority because it is strange, and we will not dismiss it because it is strange. Every step must pay rent in mechanisms and predictions. What would have to be true in measurable terms for a quantum process to matter to experience, and what would count as evidence against it? We will also explore alternative paths that use quantum in very different ways, from mathematical models of decision-making to physical hypotheses about coherence in living tissue. Each will face the same filter: identify the substrate, show a plausible timescale, explain amplification into neural activity, and offer a test that could fail. If the idea cannot be falsified, it cannot guide us. And because the question touches something older than laboratories, we will step outward into philosophy and cosmology, where some argue that consciousness is not an accident of brains, but a basic feature of reality. We will examine these views with care, separating metaphysical elegance from experimental confirmation, and resisting the temptation to let scale substitute for proof. By the end, we return to a sober kind of awe. Consciousness is profoundly real to us, and it is tightly linked to the brain in ways medicine can demonstrate. Claims of a quantum or cosmic source remain speculative, yet the search, conducted honestly, sharpens our science, deepens our philosophy, and changes how we inhabit a vast universe that is still, somehow, aware of itself through us. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We begin inside the interior universe of experience, then move through quantum reality, the classical brain, and the hidden architecture within neurons. Along the way, we test bold claims against hard constraints, until the mystery stands clearer, narrower, and more worth pursuing. You open your eyes and a world appears, already coloured with meaning and feeling. Light lands on the retina as photons and chemistry, yet it arrives as a scene, rich, immediate, and undeniably yours. The puzzle is not that brains think, but that anything is experienced at all. Matter obeys physics, yet experience arrives as a private interior universe, complete with texture, mood, and a sense of presence. That gap is where this story begins, before theories, before slogans, before easy certainty. Neuroscience has mapped many links between brain activity and reported experience, and those links are increasingly precise. We can track early perception through the visual cortex, where edges and motion are extracted in layered pathways. We can follow memory through hippocampal circuits that bind events into episodes, then distribute them back into cortex over time. We can watch attention recruit distributed control networks, including frontal and parietal regions that bias what gets processed next. We can predict choices from patterns that appear seconds before a person reports deciding, at least in constrained tasks. We can alter mood with chemistry, changing neurotransmitter balance and shifting the felt tone of a day. These are real achievements, and they matter for medicine, for psychiatry, and for understanding ourselves. But a boundary remains between correlation and explanation, and it is not a small boundary. We can say which neural events accompany pain, but not why those events feel like pain rather than silence. We can describe computations that guide speech, from phonemes to syntax to motor planning, but not why speech is heard from inside. Even when we can decode what someone is seeing from brain signals, the decoding does not become the seeing. Philosophers call this the hard problem, and it refuses to shrink into a technical footnote. The easy problems are not trivial, and they are not solved completely even after decades of progress. They ask how the brain discriminates stimuli, integrates information, stores memories, and controls behaviour across changing contexts. They include questions about timing, binding, and the way the brain stabilizes perception despite noisy inputs. They are easy, only because the answers can be framed in mechanisms and measurements, at least in principle. The hard problem asks why any of that is accompanied by a first-person point of view, why there is something it is like to be you. Documentaries often blur this line, and the blur changes the stakes in subtle ways. When a scan lights up, it can look like the mystery is ending, as if colour on a screen is the same as colour in experience. When an algorithm predicts a decision, it can sound like experience is explained away, reduced to a graph. Yet prediction is not presence, and mechanism is not meaning, even when both are impressive. A map of the brain is not the territory of feeling, and the difference matters. So we set ground rules for this series. We will separate what is well supported from what is speculative, even when speculation is tempting. We will treat consciousness as a target for explanation, not a placeholder word for whatever we cannot yet describe. We will ask what a claim predicts and what would count as evidence against it, because unfalsifiable stories are not science. We will also keep returning to the same discipline. What exactly is being explained and what is merely being associated? We also need careful definitions, because the same word hides different questions in different fields. Consciousness here means phenomenal experience, the felt quality of being, sometimes called qualia in philosophical writing. Cognition means information processing, including reasoning, memory, prediction, and control, whether or not it is accompanied by feeling. Awareness means a reportable state, when a system can access and communicate what it is experiencing, at least through behaviour or language. These distinctions sound technical, but they prevent us from sliding between problems without noticing. These distinctions matter because cognition can occur without obvious experience, at least in appearance and sometimes in measurement. A person can drive on autopilot, navigate familiar streets, and later recall almost nothing about the trip. The brain can execute skilled routines while attention drifts, suggesting that performance does not guarantee presence. In experiments, stimuli can influence choices even when subjects deny seeing them, hinting at processing without report. A computer can process information without any agreed sign of felt life, even when it mimics conversation. If we mix terms, we will mistake performance for presence, and we will overclaim what our tools can show. Now consider a guided thought experiment, grounded in clinical facts rather than science fiction. Imagine your mind as a unified theatre, one self watching one screen, with one narrator explaining what happens. Then consider split-brain patients, whose hemispheres are partially disconnected after surgery that cuts the corpus callosum. This procedure was developed to reduce severe epilepsy, and it revealed something unexpected about unity. Under certain tests, the left hand can select an object the speaking left hemisphere cannot name. The patient may even confabulate a reason, as the verbal system tries to make sense of actions it did not initiate. The point is not that two people live in one skull, or that identity is simple and divisible. The point is that unity can fracture when information channels are cut, and that fracture is measurable. Experience seems to depend on integration, and integration depends on physical connectivity across networks. The interior universe is not floating free of matter, even when it feels boundless and continuous. When communication breaks, what feels like one stream can become two partially isolated streams. Anesthesia pushes the thought experiment further because it can turn consciousness off with clinical reliability. In an operating room, the same brain can shift from vivid awareness to nothing reportable, while the body remains alive and regulated. Then it can return, often with no memory of the gap, as if time simply vanished. Different anesthetics act through different receptor systems, often enhancing inhibition or disrupting coordinated signaling. The transition can be abrupt, suggesting that awareness is a state the brain enters and sustains, not a constant background that never changes. It also raises a sharp question. What exactly is being interrupted when consciousness disappears? Sleep and seizures add more evidence of fragility, and they do so in everyday human terms. In deep sleep, experience can fade into blankness, then reappear as dreams or waking, sometimes with only fragments left behind. In rapid eye movement sleep, the brain can generate vivid scenes without external input, reminding us that experience is constructed. In absent seizures, a person can pause, lose responsiveness, and resume with no sense of interruption, as if a few seconds were cut out of reality. These shifts track brain dynamics, including changes in rhythmic coordination and large-scale connectivity. They show that consciousness is conditional, not guaranteed by mere biological life. From these facts, one conclusion is hard to avoid, even if it leaves deeper questions open. Whatever consciousness is, it depends on physical conditions, and those conditions can be disrupted by drugs, injury, and altered network states. That supports a classical picture where experience emerges from neural activity, shaped by evolution and development. Yet dependence does not automatically tell us what kind of physical story is required, or whether our current categories are sufficient. A radio depends on components, but the dependence alone does not explain the nature of the signal. Classical neuroscience models the brain as an electrochemical network, and its details are concrete. Neurons fire action potentials, synapses change strength through plasticity, and glial cells regulate the chemical environment that makes signaling possible. Large-scale rhythms coordinate distant regions, and timing can matter as much as location. Information flows through circuits shaped by evolution and learning, with feedback loops that stabilize perception and guide action. In this view, consciousness is an emergent property of complex computation and integration across many interacting parts. The hope is that, as we refine these models, the subjective side will become less mysterious. Many researchers believe this approach will eventually close the explanatory gap, and their confidence is not baseless. They argue that once we fully map the mechanisms, the mystery will dissolve, much as life once seemed to require a special essence. Others reply that even a perfect map leaves the central question untouched, because maps describe structure and function, not feeling. A complete inventory of functions still seems compatible with a world that contains no experience, at least as a logical possibility. This is the philosophical pressure point, one that keeps returning, no matter how advanced the imaging becomes. This is where the cosmological lens enters, because the brain is not outside the universe looking in. Every neuron is made of atoms, and every atom obeys the same laws as stars, oceans, and distant galaxies. If the universe is described by fundamental fields and forces, where does experience fit into that description? Is it a late-arriving byproduct of complexity, or a basic feature we have overlooked because it is not easily measured? When we ask why consciousness feels bigger than the brain, we're also asking what kind of universe could contain minds at all. Some traditions treat consciousness as fundamental, like space-time or charge, and that idea has a long history. In philosophy, forms of idealism and panpsychism have argued in different ways that mind is not a mere afterthought. In modern terms, that could mean experience is not produced from nothing, but revealed or organized by brains. It could mean the universe has an intrinsic experiential aspect, and brains are interfaces that structure it into a coherent point of view. This idea is ancient in spirit, but it demands modern discipline, because poetic claims are not enough. If consciousness were fundamental, what would that imply scientifically, beyond a shift in language? It would need clear predictions that differ from standard neuroscience, not just reinterpretations of the same data. It would need measurable consequences, not only introspective appeal or metaphysical comfort. It would need a way to connect first-person reports to third-person data without hand-waving, perhaps through constraints on information, dynamics, or physical resources. In other words, it would need to behave like a scientific hypothesis, vulnerable to being wrong. This is where quantum consciousness theories enter the conversation, partly because quantum theory sits at the base of physical explanation. They propose that classical computation is not enough, and that quantum processes play a key role in producing unified experience. Some suggest quantum coherence in the brain could support binding across distributed activity, creating a single moment of awareness. Others suggest entanglement could link mind and world in a deeper way than signals and synapses, though the details vary widely. The common claim is that something about consciousness requires physics that is not captured by classical neural models. Quantum theory already governs the small scale, and it underlies chemistry and biology in ways we often forget. It explains why atoms bond, why molecules have stable shapes, and why proteins fold into functional forms. It explains why semiconductors work, and why lasers produce coherent light, and why certain materials conduct electricity in unusual ways. So invoking quantum physics is not automatically mystical, and it is not automatically wrong. The controversy is about whether specifically quantum features, beyond ordinary chemistry, are necessary for consciousness. The seduction is obvious, because quantum theory sounds like the language of paradox when it is heard in popular form. Superposition, uncertainty, and entanglement seem to echo the strangeness of inner life, where thoughts can feel layered and possibilities can feel simultaneously present. If the mind feels bigger than the brain, perhaps it taps a deeper layer of reality, one that our everyday intuitions cannot picture. That is the hook, and it is also the danger, because hooks can replace arguments. The danger is that quantum becomes a magic word that excuses vagueness, letting mystery stand in for mechanism. Many quantum mind claims trade on metaphors rather than models, borrowing the authority of physics without respecting its constraints. If we are serious, we must ask which quantum effects, where they occur, and how they survive in warm, wet tissue. We must ask about timescales, about noise, and about whether any proposed coherence could persist long enough to matter. We must also ask how such effects would influence neural firing in a way that changes experience rather than merely existing in the background. We also must avoid a different mistake, which is dismissing the idea too quickly because it sounds strange. The history of science includes surprises, and today's impossibility can become tomorrow's engineering once measurement improves. Quantum effects once seemed confined to the microscopic, yet they now power technologies that shape daily life. The right stance is neither credulity nor contempt, because both are shortcuts. It is careful curiosity, anchored to what we can test, and disciplined by what we already know. So we clarify the central tension of this documentary, and we keep it in view as we move forward. On one side is the mainstream view that consciousness is a localized product of neural computation, emerging from coordinated activity in the brain. On the other side are proposals that experience requires deeper physics, possibly quantum, and might connect mind to the universe in a fundamental way. Both sides must face the same evidence, including clinical disruptions and measurable neural signatures. Both must answer the same questions, without changing the meaning of the words midstream. The first question is explanatory, and it is the one that keeps the hard problem alive. Can a classical network account for the qualitative feel of experience, or only its functions and reports? The second question is empirical, and it demands specificity. Do quantum processes in the brain produce distinctive signatures that we can measure, such as unusual correlations or sensitivity to particular physical manipulations? The third question is conceptual, and it is easy to state but hard to satisfy. What does it even mean for a mind to be connected to the universe, beyond the obvious fact that brains are made of matter? To keep our footing, we return to definitions and constraints, because clarity is a form of honesty. Consciousness is the felt what it is like of being, not the ability to compute or behave intelligently. Cognition is the set of operations that can be modelled and simulated, including perception, planning, and learning. Awareness is the accessible, reportable layer that experiments can probe, even if it may not capture everything that is felt. Any theory that slides between these will look stronger than it is, because it will answer one question while pretending to answer another. We also acknowledge what current science can already say with confidence, and we treat those points as boundary conditions. Consciousness varies with brain state, and it can be altered by drugs, injury, and stimulation, sometimes in remarkably specific ways. Neural correlates of consciousness can be identified, even if they are debated, and they often involve patterns of connectivity rather than a single seat of mind. These facts do not solve the hard problem, but they constrain what any solution can look like. A theory that ignores anesthesia, sleep, and disconnection is not a theory of consciousness, but a theory of something else. Now we widen the frame again, because the title of this chapter is not a metaphor, and the visuals should feel expansive. Your interior universe feels vast because it contains space, time, self, and meaning as lived realities, not as abstract coordinates. It feels unified because it binds sensations into a single scene, where sounds and colours belong to one moment. It feels private because no one else can directly access it, no matter how close they stand. The question is why such a world exists at all, and why it arrives with the certainty of immediacy. If quantum consciousness is to be more than a story, it must meet the hard problem without escaping into mysticism. It must show how quantum theory could change the explanatory landscape, rather than merely decorating it with exotic terms. It must explain why consciousness turns off under anesthesia, and why split-brain disconnection can divide access without destroying basic intelligence. It must connect cosmic claims to laboratory constraints, where measurements are limited and noise is real. Otherwise, the theory remains a mood rather than a model. There is also a deeper philosophical risk, which is confusing mystery with evidence. Because the hard problem can feel like an invitation. The hard problem is not proof that physics is incomplete, and it is not a blank check for any speculative idea. It is a sign that our concepts may be incomplete, or that explanation has layers we have not learned to connect. Quantum theory might be relevant, or it might be a distraction from better approaches that stay closer to neuroscience. The only way to know is to demand clarity, and then follow where the constraints lead. So this opening chapter sets the stakes and the rules, and it asks you to hold two thoughts at once. We will not pretend that correlates are causes, or that causes are experiences, because that is a category mistake. We will not accept quantum language as a substitute for testable models, no matter how elegant it sounds. We will follow the evidence from brain clinics to physics labs, and we will keep the central question in view. In this series, wonder is welcome, but it must answer to discipline. What if your most private experience is not sealed inside your skull, even though it feels sealed? What if awareness depends on patterns that reach deeper than neurons, into the structure of reality itself, where our current intuitions fail? Or what if the feeling of vastness is an illusion created by a finite machine, a convincing simulation of infinity? Either way, the answer will change how we think about mind, matter, and our place in the cosmos. It will also change what we think science is allowed to ask. To evaluate quantum mind claims, we first need to understand what quantum theory actually says. We also need to understand what it does not say, no matter how tempting the metaphor or how cinematic the language. That is where we go next, into the strange but precise rules that govern the smallest things, and possibly the largest questions. To evaluate quantum mind claims, we first need to understand what quantum theory actually says. Quantum mechanics is not a vibe or a metaphor, even when its language feels poetic. It is the most tested framework we have for the microscopic world, and it survives scrutiny with unnerving consistency. It began as a repair job for classical physics, not as a philosophical rebellion. Atoms should have collapsed under their own electric forces, spiraling electrons into nuclei like doomed satellites. Heated objects should have radiated infinite energy at short wavelengths, a catastrophe predicted by 19th century equations. Experiments refused to match the old formulas, and the mismatch was not small, it was structural. In the late 1800s, laboratories were filling with new instruments and sharper measurements. Spectroscopes split light into precise fingerprints, and those fingerprints did not smear into continuous bands. Instead, they arrived as clean, discrete lines, bright threads on a dark background. The universe was telling physicists that energy came in packets, whether they liked it or not. Planck introduced quantized energy as a mathematical patch, and he treated it at first like bookkeeping. He proposed that oscillators in a hot object could only exchange energy in chunks proportional to frequency. The constant that carried his name, h, looked like an arbitrary fix, until it kept appearing everywhere. Einstein treated light as particles to explain the photoelectric effect, and that move was even more radical. Shine light on metal, and electrons pop out only if the light's frequency is high enough. Brighter light adds more electrons, but it does not increase their maximum energy. That behavior makes sense if light arrives as quanta, photons, each carrying a specific energy. Bohr proposed discrete atomic orbits to fit spectral lines, and his model was a hybrid of old and new. Electrons could orbit without radiating, but only on certain allowed tracks. When they jumped between tracks, they emitted photons with specific energies. Each step felt ad hoc, yet each step worked, and the data kept tightening its grip. Then the deeper shift arrived, and it did not feel like a patch anymore. Matter behaved like waves in some experiments, and like particles in others, depending on how you ask the question. Electrons diffracted through crystals, producing patterns like ripples passing through a lattice. Photons interfered with themselves, leaving alternating bands of brightness and darkness on a screen. The world did not choose one picture, and it did not apologize. Quantum theory replaced certainty with a new kind of prediction, one that is precise without being deterministic. It does not usually tell you what will happen in one isolated event. It tells you the probabilities of outcomes across many events, and those probabilities are calculable to astonishing accuracy. Crucially, the probabilities are not ignorance in the classical sense, like missing information about hidden gears. At the center is the wave function, a compact description of a system's possible states. It is not a picture of a tiny object in space, but a mathematical object that lives in an abstract space of possibilities. It encodes probability amplitudes, not direct probabilities, and that distinction is everything. Amplitudes can add and cancel, which makes interference possible, and that is why quantum predictions differ from classical statistics. When you square an amplitude, you get a probability, and the squaring hides the sign and phase information. That hidden phase is where quantum behavior lives, like a subtle timing relationship between waves. Two possibilities can reinforce each other, or they can erase each other, even when each possibility alone would seem allowed. The result is a world where what can happen depends on how alternatives combine. Superposition is the headline concept, and it is often misunderstood because the word sounds like a metaphor. A quantum system can be in a combination of states before measurement, meaning the wave function includes multiple compatible possibilities. This does not mean it is secretly in one state and we just do not know. It means the theory represents multiple potential outcomes at once, and the interference between them can be measured. The classic example is a particle passing through two slits, and the visual is almost too clean to be real. In a darkened room, a detector screen waits like blank film. One by one, particles arrive as localized impacts, tiny dots that look perfectly classical. Yet as the dots accumulate, a striped interference pattern slowly appears, as if each particle consulted a wave. If you do not measure which slit it takes, you see that interference pattern. The pattern reflects amplitudes traveling both paths, and the paths remain coherent enough to interfere. If you measure the path, even gently, the interference disappears, and the pattern becomes two simple clusters. The experiment does not reward curiosity with extra information, it charges a price. So superposition is not a claim about human imagination or wishful thinking. It is a claim about physical behavior under controlled conditions, where isolation and measurement are engineered with care. It is verified in electrons, atoms, molecules, and engineered circuits that behave like artificial atoms. It is also fragile, and that fragility will matter later, especially when we talk about warm biological tissue. The next key concept is uncertainty, which is also easy to distort in popular retellings. Heisenberg uncertainty is not about clumsy instruments disturbing a system, as if better microscopes would fix it. It is about the structure of quantum states and the mathematics of non-commuting observables. Some properties cannot be simultaneously sharp, because the wave function cannot encode them that way. Position and momentum are the standard pair, and they reveal the logic in a simple inequality. The more precisely a state is localized in space, the less precisely its momentum is defined, and vice versa. This is not a limitation of technology or patience. It is a constraint built into the formalism that matches experiments, from electron beams to cold atoms. Uncertainty does not mean anything can happen, and it does not dissolve physics into chaos. Quantum theory is strict about what is allowed, and it limits outcomes through conservation laws and selection rules. Energy, momentum, and angular momentum still balance, and symmetries still restrict transitions. When the setup is precisely defined, the theory gives precise distributions, not vague permission. These ideas can sound abstract, so we anchor them to what they enable in the real world. Quantum mechanics explains the stability of atoms and the periodic table, because electrons occupy quantized states rather than crashing inward. It explains chemical bonding and molecular shapes, because electron wave functions overlap and form shared orbitals. It explains why solids conduct, insulate, or become superconductors, because electrons fill bands and sometimes pair up. It also explains why modern devices work at all, and the visuals here are familiar but secretly quantum. Lasers rely on quantized energy levels and stimulated emission, where photons coax identical photons into existence. Transistors rely on band structure in semiconductors, where tiny voltage changes control electron flow. MRI relies on quantum spin behavior in magnetic fields, turning atomic nuclei into measurable compasses. So quantum theory is not optional, and it is not confined to exotic laboratories. It is the foundation under chemistry, materials, and biology, even when we do not notice it. When people invoke quantum mechanics for consciousness, they are invoking a real framework with real equations. The question is which quantum features matter in brains, and whether they survive long enough to matter. Now we introduce the strangest feature that seems to reach beyond the microscopic. Entanglement links the states of two systems into a single joint description, like one-wave functions stretched across multiple objects. The parts cannot be fully described independently, even when separated. What you can say about one depends on what you can say about the other. In an entangled pair, measuring one system constrains the possible outcomes of the other. The correlations can be stronger than any classical hidden variable story allows, even if the systems are far apart. This is not a philosophical preference or a clever word game. It is an experimentally tested fact, confirmed in increasingly strict tests over decades. Einstein called it spooky action at a distance, because it offended classical intuitions about locality. He hoped quantum theory was incomplete, and he searched for deeper variables that would restore a familiar order. In 1935, the EPR argument sharpened the discomfort into a challenge. Either quantum mechanics was incomplete, or reality was stranger than locality. John Bell later derived inequalities that any local hidden variable theory must satisfy, and the logic was crisp. If outcomes are determined by local properties carried from the source, correlations have a ceiling. Experiments violated those inequalities, and later experiments closed loopholes with fast switching and distant detectors. Nature chose the quantum side, even when it looked unreasonable. Today, entanglement is not only a puzzle, it is a resource engineered on purpose. It enables quantum cryptography, where eavesdropping leaves detectable traces. It enables quantum teleportation of states, where information about a quantum state is transferred using entanglement and classical communication. It also supports quantum computing architectures, where entangled qubits explore computational spaces that classical bits cannot efficiently mimic. Entanglement does not let you send a message faster than light, and this point is not optional. The outcomes are correlated, but each outcome is locally random, like a coin flip you cannot control. You cannot choose the result you get, even if you know what correlation will appear later. Without a classical communication channel, entanglement cannot transmit usable information. This matters for quantum consciousness claims that imply telepathy or instant mind-to-mind signaling. Entanglement can correlate measurements, but it cannot carry controllable thoughts across space. Any story that ignores this is not using quantum theory correctly, no matter how many times it says non-local. The mathematics blocks the fantasy. Entanglement also does not imply that everything is mystically unified in a practical, usable sense. Entanglement is common at the microscopic level, but it is also easily destroyed by uncontrolled interactions. The environment constantly interacts with systems and scrambles phase relationships. In everyday conditions, entanglement becomes diluted into noise, like a signal drowned in static. That brings us to decoherence, the bridge between quantum strangeness and classical appearance. Decoherence is not a mystical collapse caused by awareness or human attention. It is the physical process by which quantum superpositions lose their observable interference. The system still obeys quantum rules, but the interference becomes inaccessible. When a system interacts with its environment, information about its state leaks outward. The system becomes entangled with countless degrees of freedom, including photons, air molecules, and internal vibrations. The relative phases between components become effectively scrambled from the perspective of any local observer. Interference fades for any realistic measurement, because the environment has recorded the which-way information. A useful image is a clean ripple on a pond that meets wind, rain, and debris. The ripple is still there in principle, but it fragments into patterns too complex to track. In quantum terms, the coherence spreads into the environment, and retrieving it would require reversing an astronomical number of interactions. Decoherence is not a mystery force, it is a bookkeeping avalanche. Decoherence explains why macroscopic objects look definite even though their constituents are quantum. A dust grain in air is bombarded by photons and molecules, and each collision carries away a trace of information. Its quantum coherence can vanish in extremely short timescales, depending on what superposition you try to maintain. For many macroscopic states, the times can be far below a microsecond, sometimes far below a nanosecond. The key point is not that quantum effects stop existing, because the underlying dynamics remain quantum in most formulations. The key point is that coherent superpositions become practically unobservable in open, noisy systems. The world looks classical because the quantum phases that would reveal superposition are washed out. Classical certainty is an emergent appearance, not a fundamental ingredient. Decoherence also introduces a technical but crucial idea that sounds dry until you see its consequence. Some states are robust under environmental monitoring because the environment repeatedly checks them without destroying their stability. They behave like classical pointer states, stable enough to persist and leave consistent records. Classical reality emerges as a pattern of robust correlations, records that agree across many observers and many interactions. This is where the brain enters the tension, and the visual shift from vacuum chambers to living tissue. Brains are warm, wet, and chemically active, and they never stop moving. They are full of ions, water molecules, neurotransmitters, and thermal motion. If delicate quantum coherence is needed for consciousness, it must survive this environment, or it must be constantly regenerated. We do not assume the answer yet, because assumptions are cheap and experiments are hard. We set the constraint, and the constraint is unforgiving. Any quantum consciousness model must specify where coherence lives, how long it lasts, and how it influences neural computation. It must also explain why decoherence does not erase the effect before it can matter. Decoherence solves part of the puzzle, but it does not solve everything, and that gap is important. It explains why interference disappears in practice, but it does not select one outcome as the experienced result. It does not fully answer why we perceive a single definite world rather than a blur of alternatives. The mathematics gives probabilities, yet experience gives one story. That unresolved question is the measurement problem, and it sits at the edge of physics and philosophy. Quantum theory gives a smooth evolution for the wave function, governed by the Schrödinger equation. Measurement seems to produce a single outcome, described by a different rule in many textbooks. The formalism includes both, and the relationship is still debated. One family of views says collapse is real, meaning the wave function physically reduces to one outcome during measurement. In this view, the collapse rule is a fundamental addition to the dynamics, not just a convenient summary. The challenge is to define what counts as a measurement without smuggling in vague words like observer. If collapse is physical, it should have a physical trigger. Another family of views says there is no collapse, and the wave function always evolves smoothly. All outcomes exist in a branching structure, with decoherence preventing branches from interfering. Many Worlds is the best-known version, and it treats the appearance of collapse as an effect of branching and practical isolation. The cost is conceptual weight. Reality becomes a vast tree of outcomes. A third family proposes objective collapse models, which modify quantum dynamics so that superpositions spontaneously collapse above certain mass or complexity scales. The motivation is to explain definiteness without observers as a built-in feature of nature. The price is new parameters that must be tested, and new predictions that can be constrained by precision experiments. These models invite measurement, which is why they remain scientifically interesting. There are also information-centered interpretations that treat the wave function as knowledge, belief, or an agent's bookkeeping. These approaches can clarify how probabilities enter the theory and why updating matters. They often avoid claims about what the wave function is physically, which can feel like relief. They still face the question of why outcomes are definite in experience, rather than merely definite in description. Interpretation matters for quantum consciousness claims, because some proposals lean on collapse as the missing link. If consciousness causes collapse, then awareness becomes a physical actor in measurement, not just a witness. That is a strong claim, and it must face both physics and neuroscience constraints. It must also explain why collapses align with conscious moments, rather than with ordinary interactions. If Many Worlds is right, consciousness does not collapse anything, and the story changes. Conscious experience would track a branch, not select it, and the selection becomes a matter of self-location. If objective collapse is right, collapse happens without minds, perhaps triggered by mass, complexity, or gravitational effects. In that case, consciousness is not needed to explain measurement, even if it remains mysterious for other reasons. So the measurement problem is not a license for anything, and it does not grant permission to invent new forces. It is a real open question with competing frameworks, each with different costs and benefits. Each framework has different implications for what consciousness could be doing, if anything, at the quantum level. The openness is real, but it is bounded. We now separate legitimate quantum phenomena from mystical extrapolation, because the boundary is where confusion breeds. Quantum mechanics is weird, but it is not arbitrary, and it does not bend to desire. It does not say thoughts create reality at will. It does not say intention can rewrite probabilities without a physical interaction. It does say that measurement outcomes are probabilistic within constraints, and that probabilities can interfere. It does say that interference and entanglement are real under controlled isolation, where phase information is preserved. It does say that open systems decohere rapidly, and that the environment acts like an uninvited measurement device. These are the rules any brain-based proposal must respect. At this point, a skeptic might say the case is closed, and the argument sounds straightforward. If decoherence is so fast for macroscopic objects, then brains cannot sustain meaningful quantum states. Consciousness must be classical computation, built from neurons and synapses, with no need for exotic physics. That position has weight, because it aligns with much of neuroscience, but science rarely rewards absolute certainty, especially when the frontier is measurement. There is a legitimate field called quantum biology, and it asks where quantum effects persist in living systems long enough to influence function. It does not assume magic, and it does not wave away decoherence. It looks for specific mechanisms under specific conditions, often involving structured environments that manage noise rather than eliminating it. One example is photosynthesis, where excitons move through pigment protein complexes like energy packets seeking a reaction center. Experiments suggest that energy transport can show coherence-like signatures over short times, visible in ultra-fast spectroscopy. The system may exploit structured environments to guide energy efficiently, using vibrations and couplings that keep pathways open. The effect is subtle and still actively studied, but it is not a mystical claim. Another example is enzyme catalysis, where quantum tunneling can matter in specific reactions. Protons or electrons can tunnel through energy barriers that would be classically prohibitive, especially when distances are small and masses are light. This can change reaction rates and temperature dependence, leaving fingerprints in kinetic data. It is not speculative, and it is part of physical chemistry taught to specialists. A third example is avian magnetoreception, a leading hypothesis for how some birds sense Earth's magnetic field. One model involves radical pairs whose spin states evolve coherently for a time, influenced by weak magnetic fields. Magnetic fields can shift the balance between singlet and triplet outcomes, which then changes chemical pathways. The biology is complex and the evidence is still being refined, but the mechanism is testable. These cases share a pattern that is easy to miss when quantum becomes a slogan. The quantum effects are local, short-lived and functionally constrained, and they often involve specific molecular structures. They do not require macroscopic superpositions of whole organisms. They do not imply consciousness is non-local, floating free of matter. They show that evolution can sometimes harness quantum behavior, but only within tight physical limits. Quantum biology also teaches a cautionary lesson about language. The word quantum covers many different phenomena, from ordinary bonding to delicate coherence. Ordinary chemistry is already quantum mechanical, but it is not usually what people mean by quantum mind. The question is about coherence, entanglement, and measurement-like events in neural tissue, not about the fact that atoms obey quantum rules. So we sharpen the documentary's central question, rather than expanding it into everything at once. Is consciousness a localized product of neural computation, or could it involve quantum processes that connect mind to the universe at a fundamental level? Quantum theory is real, but relevance is not guaranteed, and the burden of proof is heavy. The more extraordinary the claim, the more specific the mechanism must be. We also return to the opening hook with stricter language, because mystery should not replace precision. What if awareness is not sealed inside your skull, but is quietly entangled with reality's deep structure? If that is true, the entanglement must be defined and measurable, not merely asserted. It must do work that classical neuroscience cannot do, and it must leave traces we can look for. Now we bring the tension to its peak for this chapter, and the contrast becomes visual. Quantum effects are undeniable at small scales, and they can matter in some biological contexts, sometimes even at room temperature. At the same time, the brain is a noisy thermodynamic machine, pulsing with chemical gradients and electrical spikes. It runs at body temperature with constant molecular collisions, and it never stops interacting with itself. If a quantum state in the brain decays in femtoseconds, it cannot coordinate perception across hundreds of milliseconds. If it decays in microseconds, it might still be too fast for neural integration, where signals loop and reverberate. If it persists longer, we need a mechanism that protects it, refreshes it, or hides it from environmental monitoring. The timescale is not a detail, it is the whole game. We also need a coupling story, because isolation alone would not create experience. A protected quantum state must influence neural firing, synaptic release, or network dynamics in a way that scales up. Otherwise, it remains an isolated curiosity with no cognitive consequence, like a whisper in a hurricane. Any serious model must connect the quantum scale to the neuronal scale step by step. This is where many popular claims fail, and they fail in predictable ways. They gesture at superposition without specifying the physical degrees of freedom that would superpose. They invoke entanglement without respecting no signaling constraints, as if correlation were communication. They treat decoherence as a minor inconvenience rather than a dominant effect, even though decoherence is what makes the world look classical. But the failure of weak claims does not settle the deeper question, and it should not end curiosity. It only tells us what not to do, and that is still progress. The measurement problem remains conceptually open, even if most working physicists proceed without resolving it. Quantum biology shows that nature can sometimes use quantum tricks, and the brain might contain niches we have not yet measured well. So we set a disciplined agenda for what comes next, because discipline is how mystery becomes knowledge. We will ask where in the brain quantum coherence could plausibly persist, if it persists at all. We will ask what structures could shield or refresh it, and what physical interactions would threaten it. We will ask what timescales are required for perception and decision, and how those timescales constrain any proposal. We will also ask what evidence would count, because ideas without tests are only stories. Are there signatures of non-classical correlations in neural data, beyond what classical noise can mimic? Are there sensitivities to magnetic fields or isotopic substitutions that classical models cannot explain? Are there testable predictions that distinguish quantum proposals from standard neuroscience, rather than merely rephrasing it? So we set ground rules for this series. Wonder is welcome, but boundaries are non-negotiable, and the boundaries come from experiment. Quantum mechanics is not a blank canvas for meaning. It is a precise theory with hard constraints and surprising possibilities, and it punishes careless metaphors. The chapter ends with a narrow doorway rather than a grand conclusion, because the honest path is rarely dramatic. Quantum effects can matter in living systems under specific conditions, and we have real examples to prove it. The next question is where, if anywhere, they could live inside the brain. If they exist there, they must survive noise long enough to matter, and they must couple to cognition in a measurable way. We move forward with the tension intact, and we keep the camera steady on both sides of the divide. The universe is stranger than intuition, and the brain is stranger than we admit. The honest path is to keep both truths in view and test every bridge between them. Before quantum speculation returns, we take the classical brain on its own terms. The central question stays in frame, even as the camera moves closer to tissue and time. Is consciousness a localized product of neural computation, or something deeper? Something that computation only shadows. The brain is an electrochemical organ that runs on gradients, timing and feedback. Under a microscope, it looks like pale coral, threaded with vessels and glistening membranes. Under a voltmeter, it becomes a landscape of potentials, constantly poised to change. Neurons maintain resting potentials by pumping ions across membranes, spending metabolic energy to keep sodium and potassium unevenly distributed. That stored imbalance is not a metaphor. It is literal electrical potential energy, ready to be released when thresholds are crossed. At rest, the membrane is selectively permeable, and leak channels quietly bias the voltage toward equilibrium. The sodium-potassium pump restores the gradient after activity, moving ions against their concentrations. This is why the brain is energetically expensive, even when we sit still in darkness. It is also why oxygen deprivation disrupts awareness so quickly. Without ATP, gradients collapse and signaling fails. An action potential is an all-or-nothing pulse that travels down an axon, a brief storm of voltage that lasts only milliseconds. Voltage-gated channels open in sequence, then reset through refractory periods that enforce direction and limit firing rate. The spike is stereotyped in shape, yet it is not trivial. It is a reliable, regenerating signal that can cross long distances without fading, even through branching arbors. In many neurons, conduction speed is shaped by myelin, the insulating sheath that makes axons look like bright threads in anatomical stains. Myelination forces the spike to jump between nodes of Ranvier, accelerating transmission through saltatory conduction. Timing differences of a few milliseconds can matter, especially when many inputs converge. In that sense, anatomy becomes a clock, and white matter becomes the wiring that sets the brain's tempo. Spikes do not carry meaning alone. Meaning comes from patterns across many spikes, across many neurons, and across time. A single neuron may encode a feature, but populations encode relationships, probabilities, and context. Rate codes, timing codes, and synchrony all contribute, and the brain can mix them depending on task demands. The same spike train can mean different things depending on what other neurons are doing nearby. Computation is relational, not isolated. Synapses translate spikes into influence on other cells, and this translation is where chemistry meets electricity. At chemical synapses, vesicles release neurotransmitters into a tiny cleft, a gap so small that diffusion happens in microseconds. Receptors on the postsynaptic membrane open ion channels or trigger intracellular cascades that change excitability. Some synapses excite and some inhibit, and cognition depends on their balance. Too much excitation invites runaway activity, while too much inhibition can silence flexibility. Even this microscopic exchange is probabilistic. Vesicles do not always release, receptors do not always respond, and synapses fluctuate with recent history. The brain therefore computes with noise, yet it also uses noise as a resource for exploration and variability. When we speak of neural computation, we're not describing a pristine circuit board. We're describing a living system that stabilizes meaning through redundancy and feedback. Synaptic strength is not fixed. and plasticity is the brain's main learning mechanism. Long-term potentiation and depression adjust how strongly a presynaptic spike changes a postsynaptic cell, often through receptor trafficking and structural change. Timing matters through spike timing-dependent plasticity, where milliseconds decide whether a connection is strengthened or weakened. Neurons that fire together can wire together, but only under specific temporal rules that prevent indiscriminate reinforcement. Plasticity also has a history. The idea that connections could change with experience traces back through Hebb's mid-century proposals, and further into early physiological debates about memory traces. Later experiments in hippocampal slices gave the concept a mechanistic foothold, linking activity to durable synaptic change. Today, plasticity is not a single mechanism, but a family of mechanisms, some rapid, some slow, some local, some homeostatic. Homeostatic plasticity is the quieter counterpart to learning. Networks adjust their overall excitability to keep activity within workable bounds, preventing drift into silence or seizure. This balancing act matters for stability of perception and identity over time. Without it, learning would eventually destroy the very circuits it depends on. Neurotransmitters shape global brain state as much as local computation. Glutamate drives most fast excitation, and GABA drives most fast inhibition, forming the push-pull that sculpts cortical dynamics. Dopamine, serotonin, acetylcholine, and norepinephrine modulate gain, learning, and attention, often through slower receptors and widespread projections. These chemicals shift what networks can do, not just what they represent, like changing the rules of a game while it is being played. Dopamine, for example, is often linked to reward prediction and learning, but it also shapes motivation and the vigor of action. Acetylcholine can sharpen sensory processing and promote plasticity, especially in states of focused attention. Norepinephrine, released from brainstem nuclei, can tune arousal and responsiveness, preparing cortex for uncertainty. When these systems shift, the same sensory input can feel vivid or dull, urgent or irrelevant. The brain also signals through rhythms that are visible at the scalp and inside cortex. Oscillations reflect coordinated cycles of excitation and inhibition in populations, emerging from recurrent loops rather than from a single pacemaker. Different bands correlate with different tasks, but bands are not simple labels. They are timing frameworks that can align distant regions, allowing distributed circuits to cooperate without merging into one undifferentiated mass. Visually, EEG traces look like weather patterns, rolling waves, sudden bursts, quiet plateaus. In the cortex, local field potentials reveal layered currents, with deeper and superficial layers sometimes oscillating in different phase relationships. These rhythms are not merely epiphenomena. They can gate communication, bias plasticity, and organize when neurons are most likely to fire. Synchrony becomes important because neurons communicate in windows of excitability. If spikes arrive when a target population is receptive, influence is amplified, and downstream firing becomes more likely. If they arrive out of phase, influence is weakened, and the message dissipates into background activity. Timing can bind features into coherent percepts without a single binding center. Color, motion, and shape can be coordinated through shared temporal structure. This is where classical explanations become powerful and also incomplete. They can model how information flows, how decisions form, and how behavior is controlled across nested loops. They can also explain why anesthesia, sleep, and seizures disrupt awareness, because each state reshapes timing, connectivity, and excitability. Yet the question remains whether mechanism explains experience, or only the machinery of report. Consciousness research therefore starts with operational definitions, because science needs handles it can measure. Experiments cannot measure qualia directly, so they measure access and report, treating subjective claims as data with constraints. Subjects press buttons, give confidence ratings, or describe what they saw, while their brains are scanned or recorded. Researchers track attention, reaction times, and error patterns as proxies for awareness, knowing that proxies can mislead. This approach has roots in the history of psychology, from introspectionist traditions to behaviorist skepticism, and then to cognitive neurosciences compromise. The modern field tries to respect first-person experience while remaining experimentally disciplined. It asks what changes in the brain when experience is present and what changes when it is absent. It also asks what present should mean when experience can be faint, partial, or unstable. these tasks reveal a crucial distinction between processing and conscious access. Stimuli can prime choices even when subjects deny seeing them, suggesting that some processing remains covert. Masking can erase report while early sensory responses still occur, as if the brain registers the input but fails to stabilize it. Inattentional blindness can hide obvious objects when attention is elsewhere, reminding us that seeing is not guaranteed by stimulation. The brain can compute without the subject knowing, and that fact alone complicates naive intuition. Binocular rivalry makes this tension vivid. Two different images are presented to each eye, and perception alternates even though the input stays constant. The alternation implies that consciousness tracks internal competition, not mere sensory delivery. It also provides a natural contrast. The same stimulus can be there in the brain but absent in experience. Neural correlates of consciousness are patterns that reliably track reported experience. NCC studies compare seen versus unseen trials with matched stimuli, trying to isolate what changes when awareness changes. They manipulate masking, binocular rivalry, or attentional blink paradigms, and they look for converging signatures. They also examine sleep, anesthesia, and disorders of consciousness for constraints that generalize beyond laboratory tasks. But correlation is not explanation, and the field repeats this warning for a reason. A correlate might be a cause, a consequence, or a prerequisite that enables consciousness without containing its content. It might reflect reporting, memory, or decision processes rather than experience itself. The challenge is to separate the content of experience from the act of telling us, an experimental problem that becomes philosophical the moment we forget it. Some experiments try to reduce report confounds by using no-report paradigms. Eye movements, pupil dilation, and reflexive responses can indicate perceptual states, even when subjects remain silent. Neural signatures can then be compared with and without explicit reporting demands, searching for what persists. Even then, interpretation is contested because access and experience are hard to untangle, and because silence is not the same as absence. Across many studies, certain large-scale patterns keep reappearing. Conscious states often show richer long-range connectivity than unconscious states, as if distant regions regain the ability to exchange context. They show complex, differentiated activity rather than simple global synchrony, which can look organized yet informationally poor. They also show dynamics that can sustain information over hundreds of milliseconds, long enough for integration and decision. From this landscape, several major frameworks attempt to explain consciousness classically. They do not agree on the core mechanism, but they share a commitment that guides their predictions. Consciousness should be explainable in terms of neural computation and network dynamics, not as a supernatural exception. The mystery is approached as a scientific target, not a metaphysical stop sign. Global workspace theory is one of the most influential proposals, and it carries the flavor of cognitive architecture. It treats the brain as many specialized processors competing for access, each solving its own problem in parallel. Most processing stays local and unconscious, running quickly and quietly in sensory and motor pathways. Consciousness occurs when some information is globally broadcast to many systems, becoming available for flexible use. In this view, a conscious moment is a network-level event called ignition. Activity crosses a threshold and becomes self-sustaining across frontoparietal and other integrative hubs, rather than fading as a transient ripple. The content becomes available to working memory, decision, speech, and action planning, which is why it can be reported and used. Consciousness is less a place than a mode of access, an open channel that reorganizes the whole system. Ignition predicts signatures that researchers look for in data, and those signatures shape experimental design. Late, widespread activation should appear for seen stimuli but not unseen ones, even when early sensory responses match. Recurrent processing should matter more than feed-forward sweeps, because feedback stabilizes and amplifies. Measures like P3B components and sustained firing become candidates, though their status is debated and their interpretation depends on task structure. The theory is testable, but not settled, and its history reflects that tension. Early workspace ideas grew from models of attention and working memory, then were mapped onto neuroanatomy as imaging improved. As methods became more precise, the debate shifted toward what ignition truly marks. Is it the birth of experience, or the moment experience becomes usable for report and control? Critiques of global workspace focus on what it might be explaining and what it might be leaving out. Some argue it explains reportability and cognitive control, not phenomenal feel, because broadcast is a functional description. Others argue the neural signatures may reflect post-perceptual processes, like decision commitment or memory encoding. The theory also depends on identifying the right workspace circuits across tasks and species, which is harder than it sounds. Still, it offers a clear computational story that can be sharpened by evidence. Integrated information theory takes a different route and makes a stronger metaphysical claim. It starts from axioms about experience, like unity and differentiation, treating them as constraints rather than as byproducts. It then proposes that consciousness corresponds to integrated causal power in a system, meaning the system's present state constrains its own past and future in an irreducible way. The quantity is often summarized as phi, a measure of irreducible integration. IT predicts that a system is conscious to the extent it forms a maximally integrated cause-effect structure. It implies that some architectures have more consciousness than others, independent of behavior or verbal report. It also implies that consciousness is intrinsic to the system, not dependent on an external observer, because causal power is internal. This is why IIT attracts attention and controversy. Its claims reach beyond neuroscience into ontology. The measurement challenge is immediate and severe, and it is not just a technical inconvenience. Computing phi exactly can be intractable for realistic networks, because the number of partitions and causal relations explodes. Approximations exist, but they can diverge and depend on modeling choices such as how states are discretized. Different formulations of IIT have evolved, and critics argue the theory shifts under pressure. Supporters argue refinement is normal in a young framework, especially when it tries to be mathematically explicit. IIT also faces conceptual critiques that cut to the heart of its ambition. Some argue it assigns consciousness to systems that seem intuitively non-conscious, including simple circuits that integrate a bit of information. Others argue it can deny consciousness to systems that behave like us if their causal structure differs, which feels like a reductio. The theory risks becoming hard to falsify if phi is flexible across formulations, yet it forces a precise question about integration and intrinsic causation, and precision has a way of clarifying disagreements. Predictive processing offers a third major lens focused on perception and inference, rather than on broadcast or intrinsic causality. It treats the brain as a hierarchical prediction engine, layered from sensory cortices up through association areas. Higher levels generate expectations about sensory input, and lower levels send back prediction errors when reality deviates. The system updates to minimize error over time, effectively performing a kind of probabilistic inference. In this view, perception is not direct seeing, but controlled hallucination constrained by data. The brain infers the most likely causes of its inputs, using prior knowledge to resolve ambiguity. Attention becomes the allocation of precision, weighting some errors more than others, which changes what gets learned and what gets ignored. Action can also reduce error by changing the world to match predictions, closing the loop between perception and movement. Predictive processing explains many perceptual illusions and context effects, because expectations can dominate when sensory evidence is weak. It explains why ambiguous images flip between interpretations as competing hypotheses take turns winning. It explains why priors shape what we notice and what we miss, including why we sometimes hear words in noise. It also links to psychiatric hypotheses where priors or precision weighting may be dysregulated, altering salience and confidence. The framework is broad, and that breadth is both strength and weakness. A key question is where consciousness fits inside predictive processing, because prediction alone does not specify experience. Some proposals tie awareness to higher-level, temporally deep models that integrate across modalities and maintain a coherent world over seconds. Others tie it to the global availability of prediction error signals, which can force updates and capture attention. The framework can describe content and confidence, but it still faces the gap. Why should inference feel like anything from the inside? Why should a model have a point of view? Across these theories, a shared theme emerges around integration and recurrence. Conscious states often involve feedback loops that stabilize representations, preventing them from being overwritten by the next input. They involve crosstalk between sensory, memory, and control systems, allowing context to shape interpretation. They involve temporal persistence that outlasts a single spike volley, creating continuity from discrete events. Classical neuroscience can model these dynamics with increasing precision, and the models keep getting closer to the data. Yet the boundary line keeps returning, and it is not only philosophical theatre. Computational models can reproduce discrimination, report, and flexible behaviour, sometimes with striking fidelity. They can simulate attention, working memory, and decision thresholds, and they can predict reaction time distributions. They can even mimic signatures associated with awareness in some paradigms, including late activity and recurrent loops. But simulation does not automatically entail subjectivity, and that is the uncomfortable remainder. This is the pressure point behind the hard problem in a modern form. Classical theories often explain why we say we are conscious, because they explain access, memory, and control. They explain why information becomes globally available and why it guides action across contexts. They explain why certain brain states support narrative continuity, giving the self a story-like structure. They do not obviously explain why any of that is accompanied by felt presence, why there is something it is like. Some researchers respond that the gap is an illusion created by introspection and by misleading language. They argue that once the functions are fully explained, nothing remains to explain, because experience just is those functions described from within. Others argue that function and feeling are different categories, and one cannot reduce to the other without changing the subject. The documentary does not declare a winner here, because the evidence does not force one. Instead, it asks what kind of explanation would actually satisfy us, and why. Still, classical accounts impose constraints that any deeper theory must respect. Consciousness varies reliably with brain state and connectivity, and those variations are measurable across methods. It can be disrupted by lesions, stimulation, and pharmacology in repeatable ways, which anchors the phenomenon to biology. It tracks network dynamics over tens to hundreds of milliseconds, not just static anatomy. Any quantum proposal must reproduce these dependencies, not bypass them, otherwise it explains a different thing. We also need to be clear about what classical computation means in the brain. Neurons are not digital transistors, and spikes are not bits in a neat register, lined up like a computer bus. The brain is noisy, analog, and massively parallel, and it tolerates variability without losing function. It computes through population codes, attractor dynamics, and probabilistic inference, often using redundancy rather than precision. Classical does not mean simple, and it does not mean understood, even when the physics is not exotic. The brain's complexity can itself look like mystery from the outside, especially when we visualize its scale. Billions of neurons form networks with layered structure and recurrent loops, and each neuron can have thousands of synaptic contacts. Local microcircuits implement canonical motifs of excitation and inhibition, repeating like architectural patterns across cortex. Long-range tracks link cortex, thalamus, basal ganglia, and cerebellum into interacting control systems, each with its own timing. Consciousness likely depends on how these motifs coordinate, not on a single magic node. Thalamocortical loops are often highlighted because they regulate information flow and state. The thalamus is not only a relay, but a gate and synchronizer, shaping which signals reach cortex and when. Cortical layers send predictions downward and errors upward in many models, creating a continuous exchange across levels. During sleep and anesthesia, these loops change their dynamics, often becoming more stereotyped and less informative. The changes correlate with loss of reportable experience, suggesting that state control is not peripheral. Brain rhythms provide another window into state changes, and they are visually dramatic on screen. Under anesthesia, certain oscillations become dominant, and information integration can drop, even when neurons still fire. During deep sleep, slow waves reflect alternating up and down states across cortex, like a tide of silence and activity. During waking, faster rhythms support flexible coordination across regions, allowing quick binding and rapid switching. The details vary, but timing remains a recurring theme, almost a signature of the conscious state. Researchers also use perturbational approaches to probe causal capacity, rather than waiting for the brain to reveal itself. They stimulate cortex with TMS or electrical pulses and measure spread, tracking how activity propagates through networks. In conscious states, perturbations propagate in complex patterns, branching and recombining across regions. In unconscious states, responses can be local and stereotyped, as if the system cannot sustain rich interactions. Measures like PCI attempt to quantify this complexity, though interpretation remains debated and methods continue to evolve. These methods strengthen the classical story without closing the philosophical gap. They show that consciousness is not a free-floating essence, detached from mechanism and state. It is tied to the brain's ability to integrate and differentiate activity, and to keep that activity poised between order and chaos. They also show that awareness can be graded, fragmented, and state-dependent, rather than a simple on-off switch. The machinery matters, even if the meaning of experience remains elusive. So where does this leave the documentary's central question, now that we have walked through spikes, synapses, rhythms, and theories? Classical neuroscience explains a great deal about access, integration, and behavioral flexibility, and it does so with increasing experimental control. It maps plausible mechanisms for unity, stability, and control, and it connects them to anatomy and physiology. It offers testable frameworks that can be refined or rejected, which is the engine of science. Yet it still faces the question of why experience exists at all, and why it has the texture it does. This is the boundary between modelling and metaphysics, and it is a boundary we keep approaching from different angles. Modelling asks what computations occur and how networks implement them, from ion channels up to large-scale dynamics. Metaphysics asks what kind of thing experience is, and how it fits into the physical world if it fits at all. Science can constrain metaphysics by showing dependencies and causal pathways, narrowing what can be true. It cannot by itself guarantee that the explanatory gap will vanish, because the gap is partly about what we count as an explanation. We now make the transition that sets up the next turn of the series. If classical computation and network dynamics can explain report and control, what would count as missing? What would remain unaccounted for in principle? Quantum mind proposals claim an extra ingredient is required, something that changes the explanatory landscape. The next question is where that ingredient could enter without breaking what we already know, and without ignoring the hard-won constraints of neuroscience. We carry forward a disciplined tension rather than a verdict. The brain is a classical machine in the everyday sense, yet it is built from quantum matter, and that fact invites speculation. Classical theories may be sufficient, or they may be incomplete in principle, and the evidence is not yet a final judge. If quantum processes matter for consciousness, they must connect to spikes, synapses, and networks in a measurable way. Otherwise, they remain poetry. That is where we go next. We have treated neurons as signaling units linked by synapses and rhythms across networks. Now we move inward, because the cell's interior has structure, traffic, and timing. The camera leaves the membrane and drifts into the cytoplasm, where order emerges from what first looks like crowded fluid. Inside every neuron sits a cytoskeleton that acts like scaffolding and logistics combined. It is built from actin filaments, intermediate filaments, and microtubules that span long distances. Actin concentrates near the cell's edges and spines, shaping fine protrusions and rapid remodeling. Intermediate filaments add tensile strength, resisting stretch the way cables stabilize a bridge. Microtubules, thicker and more rigid, form long rails that can run from soma to synapse. Microtubules are hollow cylinders assembled from tubulin, a protein that comes in alpha and beta forms. Each alpha-beta pair forms a tubulin dimer, the repeating unit of the lattice. Under magnification, the dimer is not a simple bead, but a folded machine with charged surfaces and binding pockets. Those surfaces matter because they attract partners, repel rivals, and respond to the neuron's shifting electrical and chemical climate. Dimers stack into protofilaments, and protofilaments align side by side to form the tube. A typical microtubule has 13 protofilaments, though cells can vary the number. The result resembles a tiny drinking straw, only nanometers wide, with a wall made of repeating protein tiles. In neurons, these straws are packed into bundles, crossing and diverging like rail lines in a dense city. The lattice is polar, with a plus end that tends to grow faster and a minus end that is more stable. Polarity matters because directionality organizes transport and spatial layout. It also creates a kind of internal compass, allowing proteins to know which way is outward. In axons, that outward direction is usually consistent, which simplifies long-range delivery. Microtubules do not simply sit there as static beams in a building. They constantly switch between growth and shrinkage through dynamic instability, driven by GTP binding and hydrolysis. This behavior is not random chaos, but a regulated search strategy that lets the cell probe space. In many cells, dynamic instability is so vigorous that microtubules appear to flicker in and out of existence. Tubulin dimers bind GTP and add to the growing end, creating a stabilizing GTP cap. When hydrolysis catches up and the cap is lost, the microtubule can catastrophically depolymerize. In visual terms, the tube's end frays into curling strands, peeling back like a ribbon under tension. Rescue events can reverse the collapse, returning the end to growth when conditions and regulators allow. This rapid remodeling lets cells explore space, reorganize internal geometry, and respond to signals. In neurons, remodeling is constrained by long lifetimes and specialized stabilizing proteins. A mature neuron cannot constantly rebuild its entire interior without risking function, so it balances stability with flexibility, keeping major tracts intact while allowing local adjustments near synapses and growth regions. Neurons are extreme cells, with axons that can extend enormous distances relative to the soma. Microtubules provide the internal tracks that make such geometry workable and maintainable. An axon is not merely a wire, but a living corridor that must be supplied continuously. If supply fails, distal regions starve first, and the neuron's farthest connections fade before the cell body shows distress. In axons, microtubules are arranged with consistent polarity that supports one-way transport. In dendrites, polarity is mixed, reflecting different trafficking demands and local computation. This difference is not a minor detail because it determines how motors sort cargo. It also shapes where organelles pause, where vesicles accumulate, and how quickly components can be repositioned. The best established role of microtubules is intracellular transport, which is not optional for neuronal survival. Molecular motors move cargo along microtubules, carrying vesicles, mitochondria, and proteins. These motors convert chemical energy from ATP into stepwise motion, taking many coordinated walks along the lattice. Each step is small, but the cumulative journey can span centimeters or more in large animals. Kinesin generally walks toward the plus end, and dynin walks toward the minus end. With these motors, the neuron runs a bidirectional supply chain inside a single cell. Cargo is not just carried, but scheduled, queued, and sometimes rerouted when tracks are blocked. When traffic jams form, the consequences can resemble a city gridlock, except the stakes are synaptic survival. Transport is not just delivery, it is regulation of synaptic strength and excitability. Receptors, ion channels, and signaling complexes must be positioned, removed, and recycled on demand. A synapse can be strengthened by inserting more receptors into the membrane, then weakened by pulling them back inside. That choreography depends on vesicles, scaffolds, and motors arriving at the right place, at the right time. Microtubules also organize cell division through the mitotic spindle, a role obvious in dividing cells. Neurons mostly stop dividing, yet the same machinery remains central in development and maintenance. The proteins that build spindles are repurposed to build neurites, stabilize axons, and shape dendritic arbors. Evolution rarely discards effective molecular tools, and neurons inherit that ancient toolkit. During development, microtubules help shape neurite outgrowth and guidance. Growth cones integrate cues, and cytoskeletal dynamics translate chemical gradients into physical turning. In a growth cone, the leading edge fans out into a delicate veil, constantly sampling its environment. When attractive cues dominate, microtubules invade the periphery, stabilizing the new direction as the neurite advances. Microtubules interact with actin at the periphery, and the balance of forces determines extension or retraction. This is a classical story of mechanics and biochemistry, but it sets the stage. Actin can push the membrane forward, while microtubules consolidate the advance by delivering materials and resisting collapse. When repulsive signals arrive, actin contracts and microtubules withdraw, and the growth cone pivots away. Microtubules are regulated by microtubule-associated proteins that stabilize, bundle, or sever them. Tau is a famous example, and its dysfunction links microtubules to neurodegeneration. Tau can bind along microtubules, spacing them and reducing breakage under strain. Other regulators cut microtubules into pieces, which can then be transported and regrown where new tracks are needed. When tau becomes abnormally modified and aggregates, microtubule stability and transport can fail. The result is synaptic loss, metabolic stress, and network collapse that tracks cognitive decline. In imagery, the orderly rails begin to warp, and cargo that once flowed now stalls. Neurons can compensate for a while, but chronic disruption accumulates like unpaid maintenance in a fragile system. This matters for our central question because it anchors microtubules to real brain function. Whatever else microtubules might do, they already sit on critical causal pathways. They are not decorative structures waiting to be assigned meaning. They are essential infrastructure, and failures in infrastructure can look, from the outside, like failures of mind. At the same time, neurons are more than wires even at the membrane level. Dendrites integrate inputs with nonlinearities, local spikes, and compartmentalized computations that rival small networks. Electrical signals do not simply sum like numbers on a page. They interact with voltage-gated channels, dendritic geometry, and timing, producing outcomes that depend on context. A pyramidal neuron can treat different dendritic branches as semi-independent processors. Inputs can be amplified, gated, or vetoed locally before the soma ever decides to fire. In some branches, clustered synapses can trigger a local dendritic spike, a burst-like event confined to a region. That local event can then influence plasticity, tagging synapses for strengthening or weakening. Glial cells further complicate the wiring diagram that textbooks once treated as complete. Astrocytes regulate neurotransmitter clearance, metabolic support, and synaptic efficacy through local signaling. Their fine processes wrap synapses, forming a near-invisible boundary that controls chemical spillover. They also shuttle energy substrates, linking neuronal activity to blood flow and nutrient delivery. Microglia prune synapses and respond to injury, shaping network architecture over time. Oligodendrocytes tune conduction speed through myelination, adjusting timing that affects integration. Timing is not cosmetic because milliseconds can decide whether inputs cooperate or cancel. When myelin patterns change, the brain's internal rhythm can shift, altering how distributed regions bind information. Inside the neuron, signaling cascades add another layer of complexity. Calcium waves, kinase networks, and gene regulation can change excitability and plasticity over minutes to days. Calcium is especially powerful because it is both a charge carrier and a messenger. A brief calcium pulse can open pathways that reshape synapses, while longer elevations can trigger stress responses. So the brain's computation is not only in spikes between cells, it is also in state variables inside cells, where chemistry and structure store context and implement slow control. A neuron carries a history, written in protein modifications, receptor distributions, and cytoskeletal arrangements. The question becomes unsettling. How much of what the brain knows is stored in these internal configurations? This is where the microtubule hypothesis enters, not as established fact, but as a proposed deeper layer. The idea is that microtubules might participate in information processing beyond transport. It is a hypothesis that thrives in the gap between what we can easily record and what might still be hidden. It also reflects a broader scientific instinct, which is to ask whether familiar structures have overlooked capabilities. In the late 20th century, some researchers proposed that tubulin states could encode bits. They imagined microtubules as subneuronal processors, like cellular automata running inside dendrites and axons. The historical backdrop matters, because this was an era captivated by computation as a universal metaphor. Cellular automata, neural networks, and emergent complexity were in the air, and microtubules looked like a ready-made grid. The appeal was clear because microtubules are abundant, ordered, and distributed through neurons. If each dimer had multiple stable states, the computational capacity could be enormous. Even a modest number of states per dimer, multiplied across millions of dimers, suggests a vast internal state space. But large capacity is not the same as usable computation, and biology cares about control, not just possibility. Such proposals also promised a bridge between fast electrical signaling and slower biochemical memory. Microtubules could, in principle, provide an internal medium for pattern storage and transformation. In that picture, spikes would be the headlines, while microtubules would be the archive. The neuron would then resemble a hybrid device, mixing rapid signaling with deeper internal dynamics. But the leap from structure to computation is not automatic. Many biological structures are ordered without implementing symbolic or algorithmic processing any meaningful sense. Crystals are ordered, and so are membranes, yet we do not assume they compute. To move beyond metaphor, one must show how a state influences outcomes in a way that is selective, repeatable, and functionally relevant. To claim computation, one must specify states, transition rules, inputs, outputs, and coupling to behavior. Otherwise, the model becomes a metaphor that cannot be tested against alternatives. What sets the state, and what reads it out later? What noise corrupts it, and what error correction exists, if any? Without those details, the hypothesis can always retreat into ambiguity. Orch-OR will later claim that microtubules are not only classical processors, it places quantum coherence inside microtubules and ties collapse events to discrete moments of experience. This is not a small modification, because it changes the kind of physics presumed to matter. It also changes what would count as evidence, shifting attention from molecular traffic to quantum stability. That is why this chapter stays disciplined about what microtubules demonstrably do. We separate established cell biology from the speculative layer that tries to explain consciousness. The established layer is already astonishing, because it shows how a single cell can maintain a sprawling architecture. The speculative layer is alluring, because it promises an explanation for subjective unity that ordinary circuitry struggles to capture. The speculative layer begins with the tubulin dimer itself and its possible conformations. Some models suggest dipole-like properties and switchable states influenced by local electric fields. Tubulin is charged, and its distribution of charges can shift with binding partners and chemical modifications. In principle, that could create multiple preferred configurations, like a tiny switch that responds to its environment. If such states were stable and coupled, microtubules could support collective modes. Those modes could, in principle, propagate information along the lattice faster than diffusion-based chemistry. Collective modes are familiar in physics, where many small elements synchronize into waves. The question is whether the microtubule's crowded biological setting allows such synchronization to matter functionally. The more radical step is to claim that these modes can remain quantum coherent. Coherence would mean phase relationships persist across many dimers, enabling interference like a quantum computation. In plain terms, the system would behave as a coordinated whole, rather than as independent parts. That coordination would have to survive long enough to influence neural activity in a structured way. Here the physical constraints become the main battlefield. The brain is warm, wet, and ionic, and those conditions usually destroy delicate quantum phase information quickly. Warmth means constant thermal agitation, and wetness means constant collisions with polar molecules. Ionic means charges are everywhere, screening fields and creating fluctuating electromagnetic noise. Thermal noise at body temperature constantly jostles molecules and excites vibrations. Ions and water molecules collide, and electromagnetic fluctuations couple to charges and dipoles. The cytoplasm is not an empty chamber, but a dense medium where proteins drift, bind, and separate. Each encounter can scramble delicate correlations, even if the underlying structure looks orderly. Critics argue that any microtubule quantum state would decohere on extremely short timescales. They emphasize that decoherence is not an opinion, it is a calculable consequence of coupling. In quantum theory, interaction with the environment effectively leaks information outward. When that leakage is strong, the system's phase relationships vanish, and classical behavior dominates. The ionic environment is especially harsh because charges screen electric fields and create random perturbations. If tubulin states rely on subtle electrostatic differences, noise could dominate signal. Screening means that fields decay over short distances, which limits long-range coordination. It also means that any proposed dipole alignment must fight a constant storm of competing influences. Microtubules also sit in a crowded cytoplasm with proteins binding and unbinding. Each interaction can act like a measurement, entangling the system with the environment and erasing coherence. Even binding events that are biologically routine can be physically disruptive for quantum proposals. The more a structure is used for ordinary cell work, the more it is exposed to ordinary sources of decoherence. Supporters respond that biology sometimes uses structured environments to manage noise. They propose that ordered water layers, shielding by proteins, or coherent pumping could extend coherence times. The idea is not that the brain is quiet, but that it might be selectively quiet in narrow degrees of freedom. In other contexts, nature does exploit delicate effects, which keeps the door slightly open. They also argue that microtubules are not exposed like isolated molecules in solution. They're embedded in a lattice and surrounded by associated proteins that could constrain degrees of freedom. Constraints can reduce the number of ways a system can be perturbed. If the relevant variable is protected by geometry or by binding partners, coherence might last longer than naive estimates suggest. The dispute is not resolved by intuition, because both sides can tell plausible stories. The question is whether any proposed protection is quantitatively sufficient at relevant timescales. It's a question of numbers, not vibes, and numbers can be unforgiving. A mechanism that extends coherence by a factor of 10 is impressive, but it may still be far from what is required. Timescales matter because conscious integration appears to unfold over tens to hundreds of milliseconds. Any microtubule quantum effect must either persist that long or influence classical dynamics quickly and reliably. Conscious perception also has temporal structure, with binding windows and rhythmic sampling. A proposed microtubule process must fit into that timing without special pleading. If coherence lasts femtoseconds, it cannot coordinate perception directly. If it lasts microseconds, it might still be too brief unless amplified by a fast coupling mechanism. Amplification is the key word because tiny effects must become macroscopic consequences. Without amplification, even a real quantum event could be functionally irrelevant, like a whisper in a hurricane. This is why evidence becomes crucial, and why replication matters more than rhetoric. Claims must connect microtubule physics to measurable signals, and then to neural function. Ideally, the evidence would show not only that an effect exists, but that it changes behavior or perception in predictable ways. Otherwise, the story remains suspended between physics and philosophy. One line of evidence concerns microtubule vibrational modes, which are real physical phenomena. Any elastic structure has resonances, and microtubules can support mechanical and electrical oscillations. A microtubule can flex, twist, and compress, and those motions can couple to charges on its surface. In principle, mechanical vibrations could influence nearby molecules, including ion channels and binding proteins. Some experiments and models suggest resonant frequencies in the kilohertz to gigahertz range, depending on conditions and measurement methods. The open question is whether such modes are functional in vivo. In a living neuron, viscosity, attachments, and crowding can damp vibrations. Yet damping does not always erase resonance, and biology sometimes uses damped oscillations as control signals. Another line involves reported coherent-like phenomena in tubulin or microtubule preparations. Some studies claim long-lived excitations or collective behavior that looks more ordered than expected from noise. The language here is careful, because coherent-like can mean different things in different labs. Sometimes it refers to synchronized classical oscillations, and sometimes it implies quantum coherence, which is a much stronger claim. These results attract attention because they hint at non-trivial physics in biological polymers. They also attract skepticism because sample preparation, artifacts, and interpretation can mimic coherent signatures. A purified preparation can behave very differently from a living cell, and measurement tools can impose patterns of their own. The history of biophysics includes many cases where intriguing signals faded under stricter controls. Even if coherence-like signals are real in vitro, the brain is not a purified dish. The decisive test is whether similar phenomena occur in living neurons under physiological conditions. That means normal temperature, normal ionic strength, and normal biological activity. It also means showing that the phenomenon persists when the cell is doing what cells actually do, binding proteins, moving cargo, and changing states. A related approach looks for sensitivity to anesthetics, because Orch-OR links microtubules to consciousness, and anesthesia reliably abolishes consciousness. If anesthetics bind tubulin and disrupt microtubule dynamics, that could be a clue. Anesthesia is a powerful natural experiment, because it changes experience in a repeatable, dose-dependent way. The question is whether microtubules are a primary target or a downstream casualty. There is evidence that some anesthetics interact with cytoskeletal proteins and membrane components. The challenge is to show a specific microtubule mechanism that predicts anesthetic potency and conscious loss. Prediction is the standard that separates correlation from explanation. If the theory can forecast which molecules will be potent and why, it gains real scientific traction. Classical neuroscience already explains anesthesia through network-level changes in connectivity and oscillations. A microtubule theory must add explanatory power, not merely restate the same outcome. It must clarify what network models cannot, or unify disparate findings under one mechanism. Otherwise, microtubules become an extra layer that complicates without illuminating. So we ask what a microtubule layer would uniquely predict. Would it imply specific frequency signatures, specific pharmacological interactions, or specific disruptions from magnetic fields or isotopic substitutions? A unique prediction is like a fingerprint, because it can be tested and potentially falsified. Without such predictions, the idea remains a story that can adapt to any result. We also ask whether microtubule processing would be localized or global. If it is local inside cells, it must still synchronize across networks to produce unified experience. Synchronization is not trivial, because neurons are distributed across space and separated by synapses. If microtubules matter, they must connect to the known mechanisms that coordinate brain-wide timing. This returns us to the central question with tighter framing. Is consciousness a localized product of neural computation, or could it involve quantum processes that connect mind to the universe? The question is dramatic, but it is also methodical, because it demands constraints. What would we expect to observe if the answer were yes, and what would we expect if it were no? Microtubules are tempting because they are ubiquitous and ordered inside neurons. They offer a candidate substrate that is not the synapse, not the spike, and not the network diagram. They are literally beneath the surface, hidden in the cell's interior architecture. That hiddenness feeds the mystery, because it suggests a layer that standard electrophysiology might overlook. They also offer a narrative of hidden depth, where the brain's visible wiring is only the surface layer. If true, the neuron would contain an internal computational architecture that neuroscience has undermeasured. The thought is provocative, because it reframes the neuron as a multi-level system. It invites us to ask whether our usual recordings capture the cause, or only the output. But the same ubiquity can be a weakness, because microtubules exist in almost all cells. Any consciousness-specific role must explain why microtubules in neurons matter differently than microtubules in liver cells. Neurons do have unusual geometry, extreme transport demands, and intense electrical activity. Yet those differences must translate into a distinct microtubule regime, not just a poetic distinction. Proponents point to neuronal geometry, synaptic plasticity demands, and rich intracellular signaling as differentiators. Critics point to the lack of clear functional readouts tied to microtubule state transitions. A decisive readout would show that altering microtubule states changes perception or cognition in a specific way. Without that, microtubules remain essential for health, but unproven as a substrate of experience. We keep the mystery alive without letting it drift into vagueness. Microtubules are real, their biology is deep, and their disruption has serious cognitive consequences. The established story already links them to memory loss and network failure through transport breakdown. The speculative story asks whether they also contribute to the moment-by-moment fabric of awareness. The speculative claim is that they also host quantum-coherent processes that contribute to consciousness. That claim faces hard constraints from temperature, decoherence, and the need to couple to neural computation. It must also face the discipline of measurement, because consciousness theories often float free of testable detail. Here, the hope is that microtubules provide a physical handle, something we can probe rather than merely imagine. At this point, we have built the biological stage that Orch-OR needs. We have not proven the quantum drama, but we have located where it would have to occur. The stage is crowded, dynamic, and exquisitely regulated, which is both promising and perilous. In a system this busy, would coherence be protected or constantly erased? Next, we examine the theory that tries to connect microtubules to quantum gravity and to discrete conscious moments. The bridge is bold, and it will stand or fall on clarity, physics, and testable predictions. We return to the central question with sharper stakes and stricter constraints, as if the room has darkened and the instruments have been recalibrated. Is consciousness only neural computation, or does it involve quantum events tied to reality's deepest structure? Orch-OR begins as a response to the explanatory gap, not a rejection of neuroscience, and that distinction matters for how the proposal should be judged. Penrose and Hameroff accept that brains correlate with experience, yet they doubt computation exhausts understanding, because correlation alone does not specify what makes subjective feeling appear. On screen, we can watch neurons flare in fluorescent greens and reds, but the question persists. why does any of that activity feel like anything from the inside? Penrose's motivation starts with a claim about human insight and mathematical truth, a domain where right and wrong are not negotiated by culture. He argues that minds can grasp truths no algorithm can reliably generate, at least not by following a fixed set of formal rules. The idea is old in spirit, echoing debates from the early days of artificial intelligence, when optimism about symbolic programs met the stubborn complexity of understanding. Yet Penrose aims the argument at a deeper target than engineering difficulty, because he wants a principled limit, not a temporary obstacle. The argument borrows the shape of Gödel's incompleteness, reasoning without copying it directly, and the historical context is part of the drama. In 1931, Kurt Gödel showed that any formal system strong enough for arithmetic contains true statements unprovable within that system, provided the system is consistent. That result did not merely humble mathematicians, it exposed a structural boundary between truth and proof, and it still haunts any attempt to equate reasoning with formal derivation. When the documentary shows old black and white photographs of chalkboards and dense symbols, it is not nostalgia. It is a reminder that logic itself has cliffs. Penrose asks us to imagine a computer program that proves theorems by fixed rules, like a tireless clerk moving tokens according to strict instructions. If the program is consistent, there will be a Gödel-type statement it cannot prove, because proving it would require stepping outside the system's own resources. The statement is constructed to say, in effect, this statement is not provable here, and its truth is tied to the system's inability to capture itself completely. A human mathematician, Penrose says, can see that statement is true by reflecting on consistency, at least in the idealized case where the mathematician trusts the system's soundness. That reflective step seems to exceed mechanical symbol manipulation because it involves a meta-level judgment about the whole procedure. We can visualize this as a camera pulling back from the page, first the line of proof, then the entire book, then the rules that govern the book. Penrose's point is that understanding feels like that pullback, not merely the next move in the game. The intent is not that humans are infallible or always know the truth, and Penrose is careful to avoid that caricature. The intent is that understanding involves something not captured by algorithmic computation alone, especially when understanding includes the sense of seeing why, rather than merely producing outputs. In plain language, the claim is not that people never make mistakes, but that the act of grasping meaning may not reduce to rule following. Common objections arrive immediately, and they are central to the theory's controversy because they press on the argument's hidden assumptions. Critics say humans are not guaranteed consistent, so the Gödel move may not apply, and a real mathematician can hold contradictory beliefs without noticing. Others argue the reasoning smuggles in an idealized mathematician, not a real brain with limits, fatigue, and partial information. Some say the argument only shows limits of certain programs, not of computation itself, because computation can be adaptive, probabilistic, and self-modifying. Another objection points to probabilistic and learning systems that are not fixed theorem provers, and modern AI makes this objection feel less hypothetical. A mind could be computational yet not describable as one static formal system, because it can revise its own internal models and change its strategies. Critics also note that seeing a Gödel statement's truth may itself be a kind of computation, just implemented in a richer architecture than a simple proof engine. The documentary can linger here on server racks and training curves, images that suggest flexibility without invoking anything mystical. Penrose responds that the core issue is principled, not practical, and he tries to keep the focus on what computation means in the strict sense. If understanding is genuinely non-algorithmic, physics must supply a non-computational ingredient, because minds are physical systems and cannot float free of law. That is the pivot point where a philosophical dissatisfaction becomes a demand on fundamental theory, and the narration's tone shifts from debate to proposal. This is where Orch-OR pivots from philosophy to a specific physical proposal. Penrose looks at quantum theory's measurement problem and sees an opening, because quantum mechanics already contains a strange boundary between smooth evolution and definite outcomes. The measurement problem is not a fringe complaint. It is a century-old tension that has survived every technological triumph of quantum theory. We can build lasers, transistors, and atomic clocks, yet we still argue about what it means for a possibility to become an actuality. Standard quantum mechanics evolves smoothly by the Schrödinger equation, until measurement occurs, and the mathematics describes a superposition of alternatives. Then outcomes appear definite, as if the wave function collapses and the world seems to choose one result. In the lab, that choice looks mundane. A detector clicks, a screen shows a dot. But the formalism, taken literally, describes many potential dots at once. The documentary can show a double-slit pattern dissolving into individual impacts, each one a tiny punctuation mark in the dark. Many interpretations treat collapse as epistemic, meaning it reflects knowledge updating rather than a physical event, and this move keeps the equations clean. In that view, the wave function is not a real thing that breaks, but a tool for predicting what we will observe. Penrose proposes the opposite, that collapse is objective and real, and that it represents a missing piece of physics rather than a bookkeeping convention. The difference is subtle in language, yet enormous in implication. One story says reality changes, the other says only our description changes. Objective reduction, or OR, claims that superpositions of sufficiently different spacetime geometries are unstable, and that instability is not caused by observation. The instability ends the superposition, without an observer choosing an outcome, as though nature itself refuses to keep incompatible geometries suspended indefinitely. Penrose's intuition is that quantum theory assumes a fixed background time against which states evolve, while general relativity makes time part of the dynamical fabric, shaped by mass and energy. If the fabric itself is in superposition, what does evolution in time even mean, and which clock is the system supposed to use? Penrose ties this to gravity because mass energy shapes space-time geometry, and geometry is not a passive stage in relativity. If a quantum state places mass in two locations, it implies two competing geometries, each with its own curvature and its own definition of what counts as the same moment. The documentary can visualize this with a grid of space-time lines bending around two ghostly masses, both present until the theory forces a decision. The claim is not that gravity is strong in the brain, but that gravity may be the only interaction that directly concerns space-time structure. He proposes that nature cannot sustain that ambiguity beyond a calculable limit, and the limit is framed as a kind of objective threshold. Collapse happens when the gravitational self-energy of the difference becomes large enough, where self-energy refers to the energetic cost of maintaining two incompatible mass distributions. In compressed form, the timescale is set by an energy-time relation, often written as a rough inverse proportionality between the gravitational self-energy and the lifetime of the superposition. The larger the gravitational self-energy, the faster the reduction should occur, which makes Orch a candidate for explaining why macroscopic objects do not behave like giant quantum waves. This gives Orch a distinctive promise that ordinary decoherence does not provide, and the documentary needs that contrast to be crisp. Decoherence explains apparent classicality through entanglement with the environment, yet it does not select one outcome, because the global quantum state still contains all branches. Decoherence turns interference into effectively unobservable correlations, so the world looks classical to local observers, but it does not add a single, literal, and then this happened event. Orch claims there is an actual selection event built into physics, and the event is not about ignorance, but about a new law linking quantum states to space-time. Penrose frames, or as a step toward quantum gravity, where space-time itself becomes part of the quantum story, rather than a fixed arena. Collapse becomes a physical boundary between possibilities and one experienced reality, like a shoreline where a wave of alternatives breaks into a single, wet fact. The narration can slow here, because the idea is doing heavy conceptual work, or is not merely a mechanism, it is a proposed amendment to how reality updates. Orch-OR then adds a second claim that makes the theory about minds rather than particles, and this is where Hameroff's biological intuition enters. Hameroff proposes that the brain can harness OR events for cognition and experience, turning a fundamental physical transition into a functional ingredient. The brain needs a substrate that can sustain quantum states long enough to matter, because a collapse that happens in femtoseconds cannot plausibly shape perception or thought. Hameroff points to microtubules inside neurons as the candidate structure, partly because they are ubiquitous, highly ordered, and positioned deep within the cell's machinery. Microtubules are already essential for transport and cellular organization, as we established earlier, and their geometry is visually striking. They are hollow cylinders assembled from tubulin proteins, arranged in repeating lattices that resemble architectural scaffolding at the nanoscale. In microscopy imagery, they look like pale rails threading through the cytoplasm, guiding vesicles and organelles like cargo on a dense intracellular railway. Orch-OR assigns them an additional role as quantum information organizers, suggesting that their regular structure could support coordinated states rather than mere mechanical support. In this view, tubulin dimers can occupy multiple conformational or electronic states, and those states can, in principle, be treated as information-bearing degrees of freedom. The proposal often invokes dipole moments, electron clouds, and switching between slightly different shapes, where shape is not a metaphor but a physical configuration with energetic consequences. Those states can couple across the lattice, forming collective patterns like synchronized ripples traveling through a crystalline grid. The documentary can show a microtubule lattice glowing in segments, with patterns sweeping along it as if the structure were thinking in pulses. Orchestration means the brain does not wait for random collapses, and this is crucial to the theory's ambition. Neural activity, synaptic inputs, and biochemical regulation shape which microtubule states form and how they evolve, so the quantum layer is not isolated from classical physiology. Calcium concentrations change, phosphorylation states shift, and molecular motors tug on the cytoskeleton, all of which could, in principle, tune the microtubule environment. The claim is that the brain conducts these conditions, like a composer shaping when and where coherence can build, even if the notes are quantum. The claim is that microtubules integrate information at a subneuronal scale, and that this integration is not simply redundant with synaptic computation. They then influence neuronal firing by modulating membrane proteins, synaptic release, or intracellular signaling, so the quantum outcomes can bias what the neuron does next. Some versions emphasize microtubule connections to ion channel behavior, while others emphasize effects on neurotransmitter vesicle trafficking, which can alter release probability. The details vary across versions, yet the narrative beat stays consistent. Microtubules host coherent quantum evolution, then OR ends it, producing a definite outcome. That outcome is proposed to correspond to a moment of conscious experience, and the theory is explicit about what it wants to explain. Not a report, not a decision, but the felt update itself. The raw now that arrives before we describe it. The documentary can illustrate this with a human face in close-up, eyes reflecting light, while the sound design narrows to a heartbeat-like pulse. Orch-OR therefore reframes consciousness as punctuated rather than continuous, and that reframing is meant to match certain phenomenological hints. Experience becomes a sequence of discrete events, like frames that create the illusion of a stream, even though the stream feels seamless from within. The theory links frame rate to collapse time, and the proposed linkage is meant to be quantitative rather than poetic. Larger coherent states collapse faster, and smaller coherent states persist longer, setting a rhythm for conscious moments. Hameroff and Penrose propose characteristic timescales that can land in the tens of milliseconds range, and that range is chosen because it resembles known perceptual integration windows. In psychophysics, stimuli separated by tens of milliseconds can fuse into one percept, while longer separations can be distinguished, suggesting a natural temporal grain to perception. Orch-OR tries to place that grain not only in network dynamics, but in the timing of objective reductions. This is also where Orch tries to respect the constraints of classical neuroscience, because it cannot simply float above the data. Consciousness varies with brain state, so orchestration must depend on synapses, rhythms and connectivity, including thalamocortical loops and neuromodulatory tone. The proposed coupling runs both ways in the story, and the bidirectionality is part of its appeal. Neural dynamics shape microtubule coherence, and microtubule outcomes bias neural dynamics back, creating a loop that could, in principle, stabilize coherent episodes at behaviorally relevant times. If this loop works, Orch-OR claims it can explain unity and binding from inside the cell, not only across regions. Many microtubules across many neurons could participate in coordinated reductions, producing a single, integrated moment, rather than a collage of separate events. The theory also aims to address why experience feels like something, not merely why behavior is flexible, and this is where it leans into its most mysterious claim. It places qualia at the point where quantum possibilities become one actuality, suggesting that subjectivity is the interior aspect of an objective physical transition. Penrose adds a further metaphysical implication that raises the documentary's cosmic hook, and the visuals can widen accordingly, If OR is tied to spacetime geometry, conscious moments touch a fundamental layer of the universe, the level where the stage itself is being written. That does not imply telepathy or faster-than-light signaling, and Orch-OR does not require it, despite how easily audiences might drift there. The claim is subtler, that experience is linked to objective events in physics, and that those events may be woven into the same fabric that defines time and causality. At this point, the theory sounds like a bridge between brain and cosmos, built from detailed components, and that detail is both strength and liability. It also becomes vulnerable because each component can be challenged independently, and critics do not need to refute everything at once. The first major criticism targets coherence in the brain's environment, and the objection is grounded in well-established physics. Warm, wet, ionic conditions usually destroy quantum phase relations extremely quickly, because constant interactions with surrounding molecules effectively measure the system. In the brain, water molecules collide, ions drift, proteins vibrate, and thermal noise is relentless, so coherence seems fragile by default. Standard decoherence estimates suggest microtubule quantum states should collapse into classical mixtures far faster than neural timescales, sometimes in picoseconds or less depending on the assumed degrees of freedom. If so, there is nothing left for OR to do, because the state would already be effectively classical long before any gravitational threshold matters. Supporters reply that decoherence is not a single number, but depends on the chosen degrees of freedom, the coupling strengths, and the possibility of collective modes that are less exposed to the environment. They propose shielding, ordered water, or dynamical pumping that extends coherence, sometimes invoking structured layers of water near hydrophobic surfaces that behave differently from bulk fluid. Critics answer that these protections are speculative and not yet quantified convincingly in vivo, where measurements are hard and confounds are many. They also note that microtubules are busy structures with constant molecular interactions, including binding proteins, motor proteins, and mechanical stresses that could act like continuous disturbance. A second criticism targets the biological evidence for microtubules as information processors, and this criticism is as much about methodology as about plausibility. Microtubules clearly support transport and structure, yet quantum computation inside them remains unproven, and the bar for proof is high. To persuade skeptics, Orch-OR needs a clear input-output story, not only a suggestive substrate. It must show how microtubule state changes reliably influence spikes, synapses, and behavior, and it must do so with measurements that isolate microtubules from broader cellular effects. Some proposed mechanisms involve microtubule effects on ion channel gating or synaptic release probability, where tiny shifts in channel kinetics could alter excitability. Others involve intracellular signaling cascades that modulate excitability over time, such as pathways that affect phosphorylation of membrane proteins or the trafficking of receptors. The challenge is separating a plausible coupling from a demonstrated one, and the documentary can make that distinction visually explicit. A plausible coupling is a diagram with arrows that could exist, while a demonstrated coupling is a trace on a graph that changes when a specific variable is controlled. Without direct measurements, microtubules can become a convenient hidden layer for any missing explanation, and that is a danger for any theory that lives partly below current instrumentation. The narration can ask a quiet question here. When does possible become probable, and when does probable become measured? A third criticism targets the gravitational link itself, and this is where physics becomes the bottleneck. Quantum gravity is not experimentally settled, and Penrose's R formula is not derived from an accepted theory that unifies quantum mechanics with general relativity. Skeptics argue that OR could be wrong even if objective collapse exists, because collapse might follow a different rule or scale with different parameters. They also argue that collapse might occur for reasons unrelated to gravity or space-time geometry, perhaps tied to other proposed modifications of quantum theory. Supporters counter that the measurement problem invites new physics, and objective collapse models are a serious research area, not merely a narrative flourish. Penrose's version is one proposal among several, not pure fantasy, and it has the virtue of linking collapse to a physical quantity with geometric meaning. Orch-OR tries to move from speculation to science by offering touchpoints and predictions, and the documentary's tone becomes more forensic here. One touchpoint is anesthesia, because loss of consciousness is robust and reversible, and it can be induced with many chemically diverse agents. That diversity is itself a clue, because it suggests a common physical target, even if the target is not obvious. Hameroff proposes that anesthetic molecules bind in hydrophobic pockets in tubulin, and that binding would disrupt microtubule coherence and therefore disrupt orchestrated reductions. The imagery can shift to molecular renderings, with anesthetic molecules sliding into protein cavities like keys that do not quite fit. The prediction is not merely that anesthetics affect microtubules, which many molecules can do, but that anesthetic potency should track microtubule quantum disruption specifically. In other words, the theory wants a selective correlation, not a broad association, and that is a demanding standard. Evidence here is mixed and contested, and the documentary should let that uncertainty breathe without turning it into dismissal. Some studies suggest interactions between anesthetics and cytoskeletal components, yet network-level explanations already account for many anesthetic effects, including changes in thalamocortical connectivity and synaptic inhibition. Anesthesia can be described in classical terms as altered communication and altered gain control, so Orch-OR must show what it adds beyond that description. Another touchpoint is the search for measurable signatures of coherent dynamics in microtubules, because a physical theory needs physical traces. Proposed signatures include specific resonance patterns, coherence-like oscillations, or unusual noise spectra, especially if microtubules support collective modes that persist longer than expected. Some experiments report intriguing signals in vitro, including collective modes and long-lived excitations under certain conditions, and those reports keep the conversation alive. The key limitation is translating dish results to living neurons, where temperature, biochemical complexity, and constant activity may change everything. A decisive demonstration would show coherence relevant to computation at body temperature inside intact brain tissue, and it would show that disrupting that coherence changes conscious state predictably. The documentary can emphasize what decisive means, not a single surprising trace, but a chain of evidence that survives replication and alternative explanations. Orch-OR also implies a kind of temporal quantization of experience, and this implication invites careful comparison with what neuroscience already knows. If conscious moments are discrete, there may be measurable psychophysical or neural periodicities tied to collapse timing, perhaps reflected in reaction times, perceptual thresholds, or phase-locked neural events. Yet the brain already shows rhythms and sampling effects for classical reasons, including oscillations in alpha and gamma bands and recurrent processing loops that naturally create temporal structure. Any Orch-OR signature must be distinguishable from ordinary oscillations, and it must predict something that classical rhythms do not. The narration can pose a thought-provoking observation. If the brain already chops time into chunks, would we recognize a deeper clock, or would it hide inside the familiar beat? This is where earlier chapters return as constraints rather than background, and the documentary's internal logic tightens. Global workspace predicts ignition-like events and late widespread activity tied to access and report, and those predictions have a growing empirical literature. IIT predicts that integrated causal structure matters, regardless of microtubules, and it can in principle be tested by perturbational complexity measures that track how richly a system responds to stimulation. Predictive processing ties experience to hierarchical inference and precision, linking perception to error signals and the brain's best guesses about the world. Orch-OR must either reproduce these signatures or explain why they are downstream shadows, because it cannot ignore that consciousness tracks connectivity, lesions and pharmacology at the network scale. A charitable reading treats Orch-OR as a deeper layer that feeds into classical frameworks, rather than competing with them directly. Microtubule events could supply the raw moments, while workspace-like dynamics organize report and control, and predictive processing could shape which moments become salient by tuning attention and precision. In that picture, the quantum layer is not a replacement for neuroscience, but a proposed microphysical source of the spark that neuroscience then shapes into cognition. A skeptical reading treats Orch-OR as unnecessary multiplication of entities because classical dynamics already explain timing, integration, and state changes without invoking quantum gravity. The skeptical stance is not that the cosmos is boring, but that extraordinary mechanisms require extraordinary constraints, and those constraints must be met experimentally. The tension peaks because Orch-OR is unusually detailed for a quantum consciousness theory, and detail invites accountability. It specifies a collapse mechanism, a biological substrate, and a temporal structure of experience, which makes it more testable than vague appeals to quantum mystery. Yet each specification rests on premises that remain controversial, and the documentary should keep those premises distinct. The Gödel-based motivation is debated, the OR physics is unconfirmed, and the microtubule quantum biology is uncertain, so the bridge has multiple joints that could fail. Still, the theory's ambition is part of its enduring fascination because it insists that consciousness is not an afterthought but a clue. We hold the theory in the documentary's preferred posture, wonder with boundaries, and the visuals can reflect that balance. Orch-OR could be a profound unification, or it could be an elegant story built on fragile assumptions, and the difference will not be decided by mood. What matters next is not whether the idea feels mysterious, but whether it survives contact with measurement, including measurements designed by critics as well as supporters. The path forward is clearer experiments, clearer models, and clearer failure modes, because a scientific bridge must specify how it could collapse. If microtubules are central, then targeted intervention should shift consciousness in ways not predicted by synapses alone, and those interventions must be specific enough to avoid broad cellular damage. If OR is real, then collapse timescales should show gravitational dependence in controlled systems, even outside biology, because the physics should not care where it is tested. If neither prediction holds, Orch-OR may still have value as a forcing function, and the documentary can acknowledge that without retreating into vagueness. It pressures neuroscience to define what counts as explanation, and it pressures physics to confront measurement, especially the uneasy line between calculation and event. We end this chapter by widening the lens again without losing discipline, returning to the bridge metaphor with a more critical eye. Orch-OR is one proposed bridge between mind and cosmos, built from collapse and cellular architecture, and its planks are labelled with equations, proteins, and timing claims. Next, we ask what other bridges have been proposed and how they compare under the same constraints. We keep the hook alive, yet we demand that every bridge carry weight. Orch-OR is one bridge between mind and cosmos, built from collapse and microtubules, and it has a certain cinematic force, tiny structures, deep time, a sudden snap into fact. Now we widen the map, because quantum mind claims do not end there. The camera pulls back from the neuron's interior to the wider landscape of ideas, where mathematics, biology, and metaphor often share the same vocabulary. The central question stays fixed as we broaden the search, because it is the hinge on which every proposal turns. Is consciousness a localized product of neural computation, or could it involve quantum processes that connect mind to the universe? The mystery feels ancient, yet the tools are modern: ion channels, information theory, and the strange rules that govern atoms. This chapter applies one standard across competing proposals, even when their rhetoric differs. We ask for a mechanism, we ask for plausibility in living tissue, and we ask for testability. In other words, we do not ask whether a claim sounds profound, but whether it can survive contact with measurement. We also correct a recurring misconception that keeps returning in popular culture, often in the same breath as awe. Quantum does not automatically mean mystical, and it does not automatically mean mental. In physics, quantum is not a mood or a permission slip. It is a constrained framework with specific rules. Quantum theory is precise mathematics about physical systems and their measurements, and it earns its authority by predicting numbers. When the word becomes a vibe, the theory stops making predictions. The result is a haze where anything can be implied and nothing can be checked. So we separate three categories that often get blended together, especially in public conversation: quantum as math for uncertainty, quantum as physical coherence and entanglement, quantum as metaphor for wholeness. Each category can be useful, but they are not interchangeable, and confusing them breaks the chain of evidence. We begin with the least mystical and often the most successful approach, because it is disciplined about what it claims. Quantum cognition uses quantum probability to model decisions without claiming quantum brains. The visuals here are clean and abstract: vectors, angles, and probability amplitudes sliding across a dark grid. In these models, the brain is treated as classical hardware running ordinary neural dynamics, with spikes and synapses doing the work. The quantum part is the probability calculus used to fit behavior. It is a bit like using complex numbers in engineering, powerful mathematics, not necessarily a claim about hidden physical waves in the device. Human choices violate simple classical probability in systematic ways, and the violations are not random noise. Order effects appear when questions are asked in different sequences. A survey that swaps two prompts can produce a measurable shift, as if the first question tilts the mind before the second arrives. Conjunction and disjunction judgments can look inconsistent under standard Bayesian assumptions, even when people are attentive and sincere. Preferences can shift when options are framed, even with identical outcomes. The mind seems to carry unresolved possibilities, then commit abruptly when context forces a decision. Quantum probability can represent these patterns through interference terms, which are mathematical cross-terms that have no classical counterpart. A mental state is modelled as a vector, and questions act like measurements. The geometry matters. Two questions can be compatible, or they can be non-commuting, meaning order changes the result. The key move is contextuality, where the act of asking changes the state being queried, rather than merely revealing it. That resembles measurement disturbance, but it can be purely psychological. A person is not a static container of opinions. The question itself helps construct the answer. These models can outperform classical ones in certain tasks, especially when ambiguity and shifting context dominate. They can capture superposition-like uncertainty and collapse-like commitment in a compact formalism. The language is borrowed from physics, but the claim stays modest. It is about describing patterns of judgment. But the success is not evidence that neurons maintain coherent superpositions of beliefs in a literal physical sense. It is evidence that human cognition is context-sensitive and not always classically rational. The brain may be classical and still produce behavior that looks quantum-like in the statistics. Quantum cognition therefore shifts the documentary's tension in a useful way, because it separates math from mechanism. It shows that quantum mathematics can be explanatory without implying quantum mechanics in tissue. The lesson is subtle. A model can be quantum in form while the underlying hardware remains biological and warm. It also clarifies what would be required to claim more than a modeling convenience, and that requirement is where many narratives become vague. A physical quantum mind theory must specify a substrate and dynamics. It must say what in the brain plays the role of a quantum system, what counts as a measurement, and how the state evolves. That brings us to proposals that invoke entanglement directly, because entanglement is the signature phenomenon people most associate with quantum strangeness. They suggest that conscious unity could arise from non-local correlations across brain systems. The image is seductive, separated regions acting as one, bound by invisible threads. Entanglement is not just correlation, and it is not a poetic synonym for connection, even though it is often used that way. It is a specific quantum relation that produces Bell inequality violations. In the lab, it is demonstrated by carefully prepared systems whose statistics cannot be explained by any local hidden variable model. To claim entanglement in the brain, we must identify the degrees of freedom that become entangled, not merely point to neurons as a general category. We must show how they are prepared and maintained. In physics, entanglement is not assumed. It is engineered, verified, and quantified. We must also show how entanglement influences neural computation without violating no signaling, which is a hard constraint. Entanglement cannot transmit usable information faster than light. It can correlate outcomes, but it cannot be steered into a controllable message without an ordinary classical channel. The physical obstacles are immediate and severe, and they are not matters of taste. Neural tissue is warm, wet, and strongly coupled to an environment that constantly monitors it. Every collision, every vibration, every fluctuating electric field acts like an unwanted measurement. Decoherence is not a philosophical objection, it is a quantitative process with calculable timescales. Environmental interactions leak phase information and destroy interference quickly. In plain language, the delicate in-between aspects of a quantum state get smeared into ordinary probabilities. Sustained entanglement would require isolation or active error correction, and both are expensive in physical terms. It would require shielding from thermal noise and from ionic fluctuations. In engineered quantum devices, this is done with vacuum chambers, cryogenics, and exquisitely controlled materials. The brain is not built like a dilution refrigerator, and neurons are not engineered qubits, even if they can be exquisitely complex. They are metabolically active cells optimized for robustness. Their job is to function reliably amid chemical turbulence, not to preserve fragile phase relationships. Some proponents respond that certain biological niches can protect quantum states, and they are right to point out that warm does not automatically mean classical. They point to quantum biology results like excitonic coherence signatures in photosynthesis. In those systems, energy transfer can show wave-like features over very short distances and times, but those examples are narrow, fast, and tied to specific molecular structures that have been tuned by evolution for a particular task. They do not automatically scale to millisecond cognition across centimeters of tissue. A fleeting coherence in a protein complex is not yet a substrate for thought. A brain entanglement claim must bridge many scales at once, which is the real difficulty. It must connect a microscopic entangled variable to macroscopic reportable experience. The viewer should imagine a ladder from the quantum to the cognitive, where every rung must be specified rather than assumed. That bridge requires an amplification pathway that is selective and repeatable, not merely possible in principle. Otherwise, entanglement could exist briefly yet remain functionally irrelevant. Biology is full of micro-events that happen without ever shaping behavior, and physics does not grant them special status. A common confusion appears here, and needs explicit correction, because it fuels the most extravagant interpretations. Entanglement does not mean minds share thoughts, and it does not imply cosmic telepathy. The word invites that fantasy, but the equations do not. Even perfect entanglement produces correlations only when outcomes are compared later, after measurements are made. Without a classical channel, there is no controllable message. The universe can be correlated without being communicative, and that distinction is one of quantum theory's sharpest boundaries. So the question becomes narrower and more scientific, which is where it becomes interesting again. Could entanglement persist long enough to shape neural thresholds, synaptic release, or oscillatory coordination? If it could, it would need to leave fingerprints in timing, variability, or phase relationships that classical models cannot mimic. If yes, we should be able to detect interference-like signatures, because entanglement and coherence are not silent. If no, entanglement remains a background feature of matter, not a special driver of mind. The brain would still be quantum in its constituents, yet classical in its functional organization. Next, we examine a quieter pathway that often gets mislabeled as quantum consciousness, partly because it sounds like it. Randomness and noise can influence brains without any quantum computation. The visuals shift to something more biological: flickering synapses, wavering membrane potentials, and threshold lines that can be crossed by a whisper. Neurons operate near thresholds, and small perturbations can change whether a spike occurs, especially in high-gain circuits. That makes neural dynamics sensitive to noise in principled ways. A tiny fluctuation can decide whether a signal propagates, which can cascade through a network. Stochastic resonance is one such principle, and it is a well-studied effect in nonlinear systems. Adding the right amount of noise can improve detection of weak signals. It sounds paradoxical, yet it is mathematically grounded. Noise can help a sub-threshold periodic input line up with threshold crossings. In sensory systems, noise can help a sub-threshold input cross threshold at the right times, effectively boosting detectability. The result can be better performance, not worse. The brain can use variability as a resource, provided the variability is in the right range. This is counterintuitive, so it invites mystical interpretations, especially when people hear randomness and think freedom. But the mechanism is classical nonlinear dynamics, not a quantum algorithm. The improvement comes from threshold behavior and timing, not from coherent superposition. Noise itself can have many sources, and most of them are thoroughly classical at the scale of neurons. Thermal agitation, synaptic variability, channel gating fluctuations, and chaotic network dynamics all contribute. Even the brain's own rhythms can create fluctuating backgrounds that modulate excitability. Some noise ultimately has quantum origins, because matter is quantum at the base, and that is a fair point. That does not mean the brain is performing quantum computation. A quantum seed can be amplified into a macroscopic outcome without the system ever maintaining coherence. A quantum origin random event can be amplified by classical dynamics, and amplification is something biological systems do constantly. A single channel opening can shift a membrane potential and alter a spike train. Once the spike pattern changes, downstream neurons respond, and a small event becomes a network-level divergence. Yet amplification of randomness is not the same as exploitation of coherence, and the difference is not semantic. It produces variability and sensitivity, not interference patterns and entangled resource states. In physics terms, randomness can be imported without preserving phase, and phase is where quantum advantage lives. This distinction matters because it sets a boundary around what quantum can mean in neuroscience, and it prevents a slide into vague claims. Quantum can be a source of indeterminacy without being a substrate of mind. The brain may be influenced by microscopic chance while remaining computationally classical. The next family of claims moves away from specific mechanisms and into language that sounds like physics, because physics carries cultural authority. It speaks of fields, vibrations, and universal resonance. The visuals here are often luminous, rippling grids, glowing waves, and silhouettes dissolving into starlight. Quantum field theory is real physics, and it describes particles as excitations of fields that fill space. It is tested in accelerators and embedded in modern technology, from semiconductors to lasers. Historically, it emerged from the early 20th century effort to reconcile quantum mechanics with special relativity, and it did so with ruthless precision. But many consciousness discussions borrow the word field without the equations, and that is where the trouble begins. The phrase field of consciousness often functions as metaphor, not mechanism. A metaphor can be evocative, yet it cannot tell you what to measure tomorrow. A physical field theory must specify what field exists, what it couples to, and what measurable effects follow. Without that, the claim cannot be falsified. In science, unfalsifiable claims do not merely remain unproven, they remain unanchored, drifting free of constraint. Metaphors can still be psychologically meaningful, and it is worth admitting why they persist. They can express the intuition that experience feels unified and pervasive. When you look out at the world, you do not feel a patchwork of separate computations. You feel a single scene. Yet the documentary standard remains methodological, because wonder without discipline becomes a hall of mirrors. If the language cannot generate a test, it cannot compete with mechanistic neuroscience. It may still belong in poetry or philosophy, but it cannot claim the authority of physics. Some proposals try to anchor field language in electromagnetic brain activity, which is at least a concrete physical phenomenon. They suggest that the brain's EM field is the seat of consciousness. The image is compelling, billowing electrical weather around the cortex, patterns forming and dissolving like storms. The brain does generate electromagnetic fields, and those fields can influence tissue locally through known biophysics. If haptic coupling exists, though it is usually small, neurons can, in certain geometries, affect each other through extracellular fields without direct synaptic contact. But an EM field theory must still explain content, integration, and state transitions, not just presence. It must explain why anesthesia, sleep, and lesions change experience reliably. It must also explain why particular patterns correspond to particular experiences rather than merely correlating with arousal. It must also show why the same physics in other organs does not generate comparable experience, because electromagnetic activity is not unique to brains. Otherwise, the theory becomes too general to be informative. A good theory narrows possibilities, and it tells you what cannot happen. This is where measurement myths become especially damaging, because they blur what our instruments actually detect. Many viewers assume that brain imaging already reads out quantum states directly. The visuals often show a glowing brain scan and imply that the glow is a window into the deepest level of reality. EEG measures voltage differences at the scalp produced by synchronized postsynaptic currents, summed across large populations. It reflects population activity, filtered by skull and tissue. What you see as a wave is not a single neuron's secret. It is the collective rhythm of millions. MEG measures magnetic fields generated by the same currents, and it requires exquisitely sensitive sensors. It is sensitive to geometry and synchrony, not to microscopic superpositions. The signal is faint, and the interpretation relies on models of how currents in folded cortex project outward. fMRI measures blood oxygenation changes coupled to metabolic demand, which is a physiological proxy for neural activity. It is slow, indirect, and far removed from quantum state tomography. The bright spots are not thoughts glowing, but vascular responses unfolding over seconds. None of these tools measures a wave function in neurons, and none is designed to do so. They measure classical fields produced by many ions moving in bulk. The quantum underpinnings of matter are real, yet the measured variables are macroscopic averages that have already decohered into classical behaviour. When someone says an EEG detected quantum consciousness, the claim is almost always category error, not a bold discovery. The instrument cannot access that level of description. It is like using a weather satellite to infer the quantum state of a single water molecule. Wrong scale, wrong observable. This does not make imaging useless for the quantum question, and it is important not to overcorrect into cynicism. It makes imaging a constraint, because conscious state changes have clear network signatures. If a theory predicts consciousness without those signatures, it must explain why the signatures appear anyway. Any quantum proposal must be consistent with those signatures, including the way consciousness tracks integration and feedback. It must explain why conscious access tracks long-range connectivity and recurrent dynamics. It must also respect the timing, perception, report, and decision unfold on millisecond-to-second scales that are well characterized. Now, we tighten the chapter around what would actually count as evidence, because the bar is high and should be. The bar is high because the claims are extraordinary, and because the brain already has powerful classical explanations for much of its behavior. A quantum claim must therefore add explanatory power, not just add mystery. First, we would need a specified physical variable in the brain that can be coherent, and the specification must be explicit. The proposal must identify its Hilbert space, not just a location. In plain terms, it must say what the quantum bits are, how many states they have, and how they are manipulated. Second, we would need measured coherence times under physiological conditions, not under idealized laboratory extremes. The times must be long enough to influence neural computation meaningfully. If coherence lasts femtoseconds, while cognition unfolds in milliseconds, the bridge collapses. Third, we would need controlled interference-like signatures, because coherence without interference is indistinguishable from ordinary randomness. That means phase-dependent effects that disappear when which path information leaks. The hallmark is not just variability, but a structured dependence on phase and measurement context. Fourth, we would need reproducible links to cognition or conscious report, because biology is noisy and correlation is cheap. The effect must track experience changes, not just molecular activity. It should move with attention, perception, or reportability in ways that can be predicted in advance. Fifth, we would need perturbations that selectively target the proposed quantum variable, rather than globally disrupting the brain. The perturbation must shift experience in predicted directions. Otherwise, any change could be dismissed as non-specific damage, stress, or altered arousal. These criteria are demanding, but they are not anti-mystery, and they are not designed to protect orthodoxy. They are the same criteria that made quantum theory credible in physics. Historically, quantum mechanics earned its place by surviving relentless experimental cross-examination, from spectral lines to the photoelectric effect. We can imagine candidate experiments even if they are difficult, and imagining them clarifies what is missing. Look for isotope effects that change nuclear spin environments and alter cognition. Isotopes can keep chemistry nearly the same while changing spin-related interactions, which is a rare handle for separating mechanisms. Look for magnetic field dependencies that match specific spin chemistry predictions, rather than vague energy claims. Look for temperature or decoherence manipulations with controlled behavioral outputs. If a proposed quantum variable is fragile, then controlled changes in noise should alter the effect in a lawful way. Look for interference-like patterns in carefully isolated biological preparations, where confounds can be minimized, then show that the same patterns appear in vivo, not only in vitro. The progression matters. Many phenomena look exotic in isolation, then dissolve into classical explanations in the full organism. Most importantly, require replication across labs with pre-registered analyses, because extraordinary claims are vulnerable to subtle bias. Quantum mind claims have suffered from suggestive one-offs and flexible interpretation. A robust effect should survive skeptical repetition, not just sympathetic storytelling. At this point, the landscape looks less like a single dramatic bridge and more like a set of partial roads, some paved and some only sketched. Some roads are mathematical, some are physical, some are poetic. The viewer is left with a choice. Follow the roads that lead to measurements, or drift into roads that lead only to mood. Quantum cognition offers useful models while leaving the brain classical, and that is not a weakness. Noise-based accounts explain sensitivity without invoking coherence, and they fit comfortably within known neurobiology. Entanglement proposals face steep physical constraints and must show non-trivial signatures, not just evocative language. Field language must become equations or admit it is metaphor, because physics is not impressed by adjectives. The chapter's methodological pivot is simple to state and hard to honour. The more extraordinary the claim, the sharper the evidence must be. Mystery is welcome, but it must be disciplined mystery. Yet the mystery remains because the hard problem remains, and it does not vanish when mechanisms improve. Even perfect neural correlates do not automatically explain why experience exists at all. A complete map of brain activity could still leave an unanswered question. Why should any of it feel like something from the inside? So we end by turning toward the next kind of proposal, which is not about mechanisms inside matter, at least not primarily. It is about whether consciousness is fundamental. This is where the visuals often slow down: night skies, deep ocean darkness, the quiet pulse of a sleeping brain. Some thinkers argue that matter does not produce consciousness, and that consciousness is a basic feature like space-time, not an emergent byproduct. In that view, brains tune or filter it. The metaphor is not of a generator, but of a receiver, shaping and selecting rather than creating from nothing. This transition changes the rules of debate, and it changes what counts as an explanation. Instead of asking how neurons generate experience, we ask how experience and physics fit together at the base. The question becomes philosophical, yet it still touches science, because it must respect what experiments already show. The hook returns in a more careful form, stripped of the easy shortcuts. What if awareness is not sealed inside your skull, yet not because of brain entanglement tricks? What if the deepest puzzle is not which molecule collapses, but why any physical description ever comes with a first-person point of view? Next chapter, we move from mechanisms to metaphysics, and we keep the same discipline. Wonder remains, but boundaries tighten as claims grow larger. The camera holds on the threshold between brain and cosmos, then cuts to black, leaving one question hanging in the silence. We leave the neuron's interior and step into a larger claim about reality itself. The central question stays fixed, even as the camera pulls back from synapses to starlight. Is consciousness produced locally by neural computation, or is it linked to the universe's deeper structure? The hook returns with new caution, because the most seductive ideas also hide the easiest mistakes. What if awareness is not sealed inside your skull, yet not through brain entanglement tricks or vague talk of quantum magic? What if the puzzle is that physics describes structure, while experience is the structure's inside, an interior aspect that never shows up on a meter? This chapter is about metaphysical coherence, not laboratory confirmation, and that distinction is the guardrail. We can ask whether consciousness is fundamental without pretending we have measured it in a particle detector. We can also ask why consciousness tracks brain states so tightly, if it is fundamental, and why that tracking looks so lawful. We begin with panpsychism, the view that experience is a basic feature of matter. It says the world is not made of dead stuff plus a miracle at some late evolutionary moment. It says even simple systems have proto-experiential aspects, however minimal, something like a faint what it's like, not a tiny person. The claim is not that rocks daydream, but that the ingredients of reality are not wholly devoid of interiority. Historically, this idea has surfaced whenever mechanistic pictures felt incomplete. Spinoza's monism, Leibniz's monads, and later neutral monist proposals all tried to avoid a sharp split between mind and matter. In the 19th century, as physics grew more mathematical, substance became less intuitive, and philosophers kept asking what, exactly, the equations were about. Modern panpsychism is usually more modest, borrowing the language of fundamental properties rather than theology. The motivation is the hard problem we set in Chapter 1 and never resolved. Neural correlates map what changes with experience, and they do it with increasing precision. We can watch perception track recurrent activity, and we can watch attention reshape cortical gain, yet we still do not see why any of it is felt. They do not explain why any mapping is experienced, rather than merely executed in the dark. Panpsychism tries to remove the jump from non-experience to experience. If the basic furniture of reality already includes a primitive experiential aspect, then consciousness does not appear from nowhere. Instead, it becomes a question of organization, scale, and integration, how the faint becomes vivid. The mystery shifts from creation to arrangement, which is not easier, but it is different. Panpsychism comes in careful and careless forms, and we keep them separate. Careful versions treat micro-experience as a primitive property, like charge or spin, and they accept that primitives are not explained further. They aim to be as disciplined as physics is with its own fundamentals, even when the fundamentals feel strange. Careless versions treat it as a vibe that explains everything and predicts nothing, which is not an explanation at all. A key pressure point is the combination problem, and it is not a minor technicality. If electrons and molecules have micro-experiences, how do they combine into one unified mind? How do many tiny perspectives become the single scene you live inside with one center of gravity? Without an answer, panpsychism risks trading one miracle for another. We can state the problem without mocking it, because it is a genuine conceptual obstacle. Physics combines masses into a larger mass, and charges into a net charge, by clear mathematical rules. Experience does not obviously add that way, because subjectivity seems to have a single point of view. One, here, not a committee. If there were many separate insides, why would they ever fuse into one inside? Even the brain makes the problem vivid when we look closely. Billions of neurons fire in parallel, and yet you do not experience billions of separate flickers. You experience one coherent field stitched together across time, with a stable sense of me riding inside it. On screen, the camera can glide across cortical layers like a city at night, where countless lights still read as one skyline. Some panpsychists propose that certain kinds of integration create a new subject. They borrow language from information integration and causal unity, echoing IIT's emphasis on irreducible structure. They point to feedback, recurrence, and mutual constraint, patterns that cannot be decomposed without losing something essential. Yet the step from integrated function to unified feeling remains the very gap they hope to close. Others try to sharpen the proposal with constraints that sound almost engineering-like. They suggest that when microsystems enter the right kind of mutual dependence, a higher-level subject becomes real. The cost is that the theory must define that dependence in non-metaphorical terms, what counts as dependence, and why. Otherwise, dependence becomes a label we paste onto the mystery. Notice what is being asked because it is easy to miss. We're not merely asking how signals integrate, which neuroscience already studies. We're asking how many becomes one in the first-person sense, without simply declaring that it does. The question is not about coordination alone, but about ownership. Who, if anyone, owns the integrated scene? A different move avoids combination by changing the direction of explanation. Cosmopsychism says the universe is the primary subject, and individual minds are partial localizations. Instead of building minds upward from particles, it derives minds downward from a cosmic whole, like eddies in a single ocean. The metaphor is fluid, but the ambition is structural. Cosmopsychism can sound mystical, yet it is often framed as a structural solution to a structural problem. If there is one fundamental subject, there is no need to fuse countless micro-subjects into unity. The hard part becomes explaining how one mind yields many, without turning into pure metaphor or hand-waving. What does partition mean when the thing being partitioned is a point of view? Here the boundary between philosophy and physics becomes delicate, because cosmology already treats the universe as a single system in some equations. We model the cosmos with a global wave function in some approaches, or with a single space-time manifold in general relativity. That mathematical unity does not automatically imply a unified experience, and we must not smuggle that in. A single equation can describe a system that has no inner life at all. It helps to picture the visuals the way a cosmologist does. A dark sky becomes a grid of measurements, a map of temperature anisotropies, a spectrum of fluctuations. The universe looks like a dataset, and the temptation is to imagine a reader behind it, yet the equations do not require one. The camera can linger on the CMB's mottled oval, where tiny speckles carry the memory of primordial physics. We now bring in information-first views because they are often presented as a bridge between mind and matter. Some thinkers argue that information is more basic than matter, and consciousness is tied to information's organization. The claim can be compatible with physics, or it can quietly replace physics with a new metaphysics. The difference often hides in a single word, information, about what and for whom. We need to define information before we let it carry metaphysical weight, because the same word hides different technical meanings. In thermodynamics, information is linked to entropy and the counting of microstates. In Shannon theory, information measures uncertainty, reduction in messages, not meaning and not experience. In everyday speech, we slide between these senses without noticing the friction. In thermodynamics, entropy is not a mood of disorder, despite the popular metaphor. It is a measure of how many microscopic configurations correspond to the same macroscopic description. When you say, "This gas has this temperature and pressure," you're ignoring an astronomically large set of micro details. That ignorance is not a flaw, but a feature of how macroscopic laws work. That is where information enters, as a bookkeeping of what you do not know. Lower entropy can mean fewer compatible microstates, which corresponds to more constraints and, in a sense, more specification. In statistical mechanics, those constraints can be written down precisely, and they predict heat flow and equilibrium. But specification is not sensation, and constraints are not consciousness. In Shannon's framework, the key quantity is the average surprise of symbols. A string with high Shannon entropy is less predictable, and it carries more information in the technical sense. Yet a random radio hiss can be information-rich while being meaningless, and meaning is not guaranteed by statistics. The camera can show scrolling bits that look profound, then reveal they are just noise. This distinction matters because it blocks a common slide. Shannon information can increase when a random sequence becomes less predictable, even if it means nothing to anyone. Experience is not just unpredictability, and meaning is not just bits arranged in a clever pattern. If we forget that, we start treating information as a synonym for mind. Quantum theory also uses information-like language, and it can confuse the issue with familiar words. A quantum state encodes probabilities for measurement outcomes, and measurement updates those probabilities. That formal update is not automatically a conscious update, even if the words sound similar in everyday speech. The mathematics tracks correlations, not the feeling of learning. When physicists talk about information in black holes or quantum fields, they mean constraints on correlations and recoverability. They mean what can, in principle, be reconstructed from other degrees of freedom, given the laws. They do not mean a universe that knows or a cosmos that feels, unless they argue for that extra step. The burden is to show how recoverable becomes experienced. The history here is worth remembering because it shaped the metaphors we inherit. Maxwell's demon, Szilard's engine, and Landauer's principle tied information to physical cost, showing that erasing a bit dissipates energy. Those arguments were not mystical but brutally mechanical, grounded in heat and work. That is profound, but it is still about thermodynamic accounting, not inner life. Still, information-first approaches have a real appeal, and we should not pretend otherwise. They fit a world where physical laws look like rules for transforming states, and where symmetries constrain what can happen. They also resonate with neuroscience, where brains are organized around prediction, compression, and control. When the brain minimizes error, it looks like an engine that trades uncertainty for stability. On screen, this is where the imagery shifts from neurons to networks. We see cascading activity, recurrent loops, and error signals flowing like weather fronts across cortex. The brain looks less like a calculator and more like a self-updating model of its own world. In a slow pullback, the network becomes a living topography, ridges of activation rising and dissolving. But an information-first view faces a hard question of its own, and it cannot be dodged by clever definitions. Why should information processing be accompanied by experience at all? If consciousness is fundamental, information may describe its structure, yet it does not explain its existence. If consciousness is not fundamental, information still does not tell us why it appears. Now we widen to cosmology, because the word universe invites grand conclusions too quickly. The early universe was hot, dense, and remarkably simple in large-scale description. It was close to thermal equilibrium, with small fluctuations that later became structure, like faint ripples that never fully vanished. In that era, the laws of particle physics set the menu of what could exist. Those fluctuations are not just poetic. They are measured in the cosmic microwave background as tiny temperature differences, roughly 1 part in 100,000. From that subtle unevenness, gravity had something to amplify, and time had something to work with. The image is almost gentle, yet it is the seed of every galaxy. As the universe expanded, gravity amplified tiny differences. Matter clumped into stars and galaxies, and chemistry diversified as heavier elements formed in stellar furnaces. Complexity emerged through known dynamics, without requiring that consciousness was inevitable, or that the cosmos was aiming at minds. The story is lawful, and that lawfulness is part of its beauty. This is a key boundary for the chapter, because it separates emergence from inevitability. Complexity can grow from simple rules, and we see that in physics and computation. The existence of complexity does not by itself imply that experience is everywhere, or that it is fundamental. A rich pattern can be empty of subjectivity. We can say this plainly, because plainness is a kind of honesty. A hurricane is complex, with swirling vortices and feedback loops, yet we do not assume it has a point of view. A crystal is highly ordered, with repeating lattices, yet order alone does not guarantee feeling. Complexity and consciousness can rhyme, but they are not the same word. Even living systems do not settle the issue by themselves. Cells process signals, maintain boundaries, and regulate internal variables, and yet we do not automatically attribute consciousness to every metabolism. The question is not whether something is complicated, but whether complication entails an inner perspective. If it does, where is the threshold, and why there? So if panpsychism is true, it cannot rest on complexity alone. It must claim that experience is present even where complexity is low, perhaps as a minimal property of matter. That makes the view bold, and it also makes it hard to test, because the simplest systems cannot report. We are left inferring interiors from exteriors, which is always perilous. At this point, anthropic reasoning enters, because it is often misheard as consciousness creating reality. In cosmology, the anthropic principle is usually a selection effect, not a magical force. We observe conditions compatible with observers, because incompatible conditions contain nobody to observe them. The principle is less a cause than a filter. This can feel circular, but it is closer to a statistical filter. If there are many possible cosmic histories, then only a subset permits long-lived stars, stable chemistry, and planets with time for evolution. The anthropic move does not explain why the universe is this way, but it can constrain what we should expect to see. It tells us what cannot be surprising, given that we exist to be surprised. Cosmologists also use the word observer in a technical way, and the mismatch with everyday language is a source of endless confusion. An observer can be any system that interacts and records, even a detector, a photographic plate, or a dust grain that becomes correlated. That is not the same as a conscious mind having an experience. In the lab, observation can mean nothing more than an irreversible record. This distinction loops back to Chapter 2's measurement problem, where words can mislead as much as equations clarify. Quantum measurement involves definite outcomes in macroscopic records, and those records can be modelled as physical correlations. Whether that requires consciousness is an extra claim, not part of standard quantum mechanics. The formalism works whether anyone is watching. We now address links people often cite, starting with the holographic principle. In physics, holography is a conjectured equivalence between theories, where bulk gravity can be described by boundary degrees of freedom. It is about how information scales, not about minds living on a cosmic screen. The principle grew from black hole thermodynamics, where entropy seems to scale with area. The visual metaphor is irresistible, because a hologram suggests hidden depth encoded on a surface. Yet the technical claim is more austere, tied to entropy bounds and to how many degrees of freedom fit in a region. It tells you something about the bookkeeping of quantum states in gravitational settings. It does not tell you that the bookkeeping is being felt. Holography can inspire metaphors about reality as encoded, yet the physics stays operational. It constrains entropy, correlation, and the accounting of quantum states in gravitational settings. It does not imply that the universe is a thought, or that experience is fundamental unless we add a separate argument. The metaphor is a door, not a destination. Next is the simulation argument, which is philosophy, not cosmology. Even when it borrows computational imagery, it asks whether advanced civilizations could run ancestor simulations, and whether we might be in one. Even if the argument were sound, it would not show that consciousness is cosmic or built into physics. It would only relocate the hardware. A simulation could contain conscious beings, or it could contain behavioral zombies, depending on one's theory of mind. The argument shifts the substrate from atoms to computation, yet it does not solve the hard problem. It also struggles to yield testable predictions, because many simulations can mimic any data we can collect. The camera can show a world rendered in pixels, then dissolve into the same world made of atoms. People also cite quantum non-locality, as if it implies a universal mind, and the leap is understandable but not licensed. Entanglement produces correlations across distance, and those correlations can violate classical intuitions. Yet it does not transmit controllable messages, and no signaling remains a hard boundary that keeps physics causal in the operational sense. Connection is not communion. So where does that leave the universal network idea, the sense that everything is connected in a way that might be mental? It can be stated in two distinct ways, and we must keep them apart. One is a bridging claim about ontology, saying consciousness is fundamental like space-time. The other is an empirical claim, saying this fundamentality changes measurable brain behavior. A universal consciousness view can be internally coherent, yet still unfalsifiable, and that matters for how we treat it. If every possible observation is compatible with it, then it explains nothing in the scientific sense. To become science, it must risk being wrong, and it must specify what would count against it. Otherwise, it becomes a story that always wins. What would that risk look like in practice, rather than in slogans? It could predict specific deviations from standard neuroscience, such as consciousness without the usual integration signatures, or without the expected thalamocortical dynamics. It could predict new physical effects tied to conscious states, beyond ordinary physiology and beyond placebo-like confounds. It could also specify boundary conditions, where consciousness should persist despite neural disruption. It could also connect to objective collapse ideas from Chapter 5, but only with care and with quantitative commitments. If consciousness is tied to collapse, then collapse rates should be measurable in non-biological systems under controlled conditions. If collapse is not measurable there, the brain claim loses its physical anchor, and the story becomes selective. A theory that only works in brains is not yet a theory of physics. We should also be honest about the strongest counterpressure, because it is not philosophical but clinical. Consciousness tracks brain state with brutal reliability in the hospital and the lab. Anesthesia, seizures, lesions, and disconnection syndromes change experience in lawful ways, and those laws are not subtle. The data is not occasional, it is routine. Anesthetics, for example, do not merely turn off neurons like a switch. Many alter receptor dynamics, change inhibition, and disrupt long-range coordination, which is consistent with theories that emphasize integration and broadcast. Some increase inhibitory tone through GABAergic mechanisms, while others disrupt NMDA-mediated excitation. Different routes, similar experiential collapse. When the chemistry shifts, the field of experience narrows, fragments, or disappears, and it does so on a timetable. Split brain results still matter here, because they show how unity depends on physical integration. If consciousness was simply everywhere and always unified, severing the corpus callosum should not produce two semi-independent streams. The data suggests that whatever consciousness is, it is organized by brain architecture, not merely accompanied by it. The mind's oneness appears engineered. This creates a tension that panpsychism and cosmopsychism must address, not evade. If consciousness is fundamental, why does it appear gated by thalamocortical loops and neuromodulators? Why does it fade with deep sleep and vanish with sufficient anesthesia, as if a circuit has lost coherence? If the cosmos is conscious, why does the local window close so cleanly? One response says brains do not create consciousness, they shape access to it, and that phrasing is carefully chosen. The brain becomes a filter or a receiver, selecting and structuring a wider field. Yet this metaphor must face the clinical constraints, because filters still have mechanisms and receivers still require coupling. A receiver with no channel is only an image. If the brain is a receiver, what is the carrier signal, and how does it couple to neurons? How does the coupling respect energy constraints, timing constraints, and the known pharmacology of consciousness? Without a coupling story, the receiver idea remains poetry, and poetry cannot substitute for causal detail. The question is not whether the metaphor is beautiful, but whether it can be specified. Another response says the fundamental consciousness is minimal, and brains amplify it into rich experience. That can reduce the mystery of emergence, because it avoids creation from nothing. Yet it reintroduces the combination problem in a new form, amplification of what, into what, and by what measurable steps. If amplification is real, it should leave a trace in dynamics. We can also connect this to Chapter 3's frameworks without forcing a conclusion, because frameworks can illuminate different edges. Global Workspace explains access and report through broadcast dynamics, emphasizing what becomes globally available. Predictive processing explains perception as controlled inference, emphasizing the brain's generative models and error correction. Both can be described in computational terms, yet both still face the question of why computation feels like anything. IIST explains consciousness as integrated causal power, emphasizing intrinsic structure rather than outward behavior. Panpsychism sometimes aligns with IIT's idea that experience tracks intrinsic causal structure, even in simple systems. Cosmopsychism sometimes aligns with a top-down unity that local systems inherit, though inheritance is still a metaphor until defined. The alignments are suggestive, but suggestion is not evidence. None of these alignments is a proof, and none removes the need for discriminating tests. They are maps, not territory, and maps can be drawn in many projections. The question is which projection predicts the next observation, and which merely redescribes what we already know. A theory earns its place by narrowing the space of possibilities. Now we tighten the chapter's discipline, because the stakes are rising as we approach the series climax. Metaphysical views can guide what questions we ask, and what we count as an explanation, which is not trivial. They can also reveal hidden assumptions, like whether matter is defined only by what it does. They cannot replace evidence, and they cannot override constraints, even when the constraints feel spiritually inconvenient. So we draw a clean line between coherence and confirmation, and we hold it steady. Panpsychism and cosmopsychism may be coherent responses to the hard problem, offering ways to avoid brute emergence. Information-first views may be coherent ways to describe physical law, emphasizing transformation and constraint. None is confirmed by current neuroscience or cosmology. We also admit a subtler point, because the debate is not simply fundamental versus biological. Even if consciousness were fundamental, brains could still matter decisively, shaping what that consciousness becomes. Fundamental does not mean causally irrelevant, and it does not mean free from biology. The local machinery could still be the difference between a whisper and a world. A fundamental property can still depend on organization to become the kind of thing we recognize as a mind. Charge is fundamental, yet circuits matter, and the same electrons can light a bulb or store a memory. Spin is fundamental, yet materials matter, and collective behavior changes what is possible. Structure does not create the property, but it determines what the property can do. That analogy is tempting, and we should handle it carefully because analogies can hypnotize. Charge and spin are measured with clear instruments and equations, and their roles are specified in predictive models. Consciousness is known directly from the first person, and indirectly through report and behavior, which makes its measurement conceptually different. We are both the instrument and the thing being measured. This mismatch in access is part of the mystery, and it is also part of the methodological trap. We can always project experience outward, because we know it intimately in ourselves, and because empathy is built into our cognition. Science demands that we separate projection from inference, and that we justify the inference with constraints. The question is not whether projection happens, but whether we can discipline it. So we end the chapter by returning to the central tension, and we let it remain tense. The universe may be stranger than our categories, and consciousness may be deeper than computation, or deeper than any current model. Yet the tight coupling between experience and brain state is the boundary any cosmic theory must respect, not explain away. If a view cannot honor that coupling, it is not yet a contender. To stay grounded, we now draw the boundary line more sharply. We ask what established physics actually commits us to, and what established neuroscience can already explain. Then we mark where speculation begins, and why that boundary matters when wonder starts to feel like proof. The next step is not to shrink the mystery, but to measure where the mystery truly lives. Next chapter, we return to the hard edges of the standard model and the hard edges of brain data. We keep wonder alive, but we stop letting it blur the difference between a worldview and a test. We have chased consciousness from synapses to microtubules to cosmic metaphysics, and now we reach the boundary where science is strongest. This chapter is a reality check that keeps the wonder intact, because boundaries are where better questions are born. In a documentary, boundaries are not dead ends. They are the sharp edges where imagination must negotiate with measurement. The central question returns with less romance and more precision. Is consciousness a localized product of neural computation? Or could it involve quantum processes that connect mind to the universe? The phrasing matters, because quantum can mean a strict physical mechanism or a poetic label for mystery. If we want honest speculation, we have to keep those meanings separated, even when the story feels tempted to blend them. Start with what physics already explains with brutal accuracy. The Standard Model is not a philosophy of everything, yet it is a machine for predicting outcomes to many decimal places. It is the distilled result of a century of collisions, detectors, and mathematical consistency checks. It is also a reminder that nature often rewards the theories that are simplest in their assumptions and strictest in their bookkeeping. It says the world is made of quantum fields, and particles are excitations of those fields. In this view, an electron is not a tiny billiard ball travelling through emptiness. It is a stable ripple in the electron field, carrying charge, mass, and spin as quantized properties. Even the vacuum is not truly empty. Fields fluctuate, and those fluctuations leave fingerprints we can measure. Electrons, quarks, photons, gluons, and their relatives are the cast, not because we like them, but because experiments demand them. The list is not aesthetic, and it is not optional. It is the smallest set we have found that consistently explains what detectors record across energies and environments. When new particles appear, they are not welcomed by philosophy. They are forced into the script by data. It organizes matter into fermions and forces into gauge bosons, with the Higgs field setting masses through symmetry breaking. Fermions with half-integer spin obey the Pauli exclusion principle, which is why matter has structure and why atoms do not collapse. Gauge bosons with integer spin mediate interactions through exchange processes that can be calculated in perturbation theory. The Higgs mechanism is not just a name, it is a specific way a symmetric equation produces an asymmetric world. It unifies electromagnetic and weak interactions, and it describes the strong interaction through quantum chromodynamics. Electroweak unification means that at high energies, the photon and the W and Z bosons emerge from a single mathematical framework. Quantum chromodynamics explains how quarks are bound by gluons into protons and neutrons, and why we never see isolated quarks in nature. Confinement and asymptotic freedom sound abstract, yet they are the reason nuclei hold together, and the reason high-energy collisions produce jets. Its predictions are not vague. It nails the electron's magnetic moment, scattering cross-sections, atomic spectra, and the behavior of semiconductors that run our entire technological civilization. The electron G-factor is measured to extraordinary precision, and the theory matches it with equally extraordinary precision. When accelerators smash particles together, the Standard Model predicts the statistical distribution of outcomes, not just a general trend. Even the glow of a screen and the timing of a processor depend on these quantum rules behaving exactly as advertised. It also sets hard constraints on what can influence what. Interactions are local in the field sense, conservation laws hold, and no signaling survives even when entanglement shocks intuition. Locality here does not mean no correlations at a distance, because entanglement creates correlations that are real and testable. It means you cannot use those correlations to send controllable messages faster than light. The universe allows strange coordination, yet it blocks convenient shortcuts. Notice what is missing, because the missing pieces are where stories rush in. Consciousness is not a variable in the Standard Model's equations, not because it is denied, but because the model tracks fields and interactions, not first-person experience. The Standard Model tells us what a detector will register when a field is perturbed. It does not tell us what it feels like to be the one reading the detector. In the Standard Model, there is no term for felt redness, no operator for meaning, and no parameter for a point of view. There is no symbol you can plug in for the taste of salt or the ache of nostalgia. The model predicts detector clicks, not what it is like to see the click. That is not a failure of the equations on their own terms. It is a statement about what the equations were built to do. That gap can be interpreted two ways, and the difference matters. One view says consciousness is emergent at higher levels, like temperature emerging from molecular motion. Temperature is not in the fundamental equations either. yet it becomes real and useful when you describe many particles at once. Another view says consciousness is fundamental, and the model is incomplete in principle, meaning experience is not merely a pattern but a basic ingredient. Either way, the standard model does not give quantum consciousness a free pass. It gives constraints that any physical mechanism must respect, including energy scales, coupling strengths, and decoherence from uncontrolled environments. If a proposed mechanism requires exotic particles, it must survive collider limits and astrophysical bounds. If it requires long-lived coherence in warm, wet tissue, it must survive the known rates of environmental interaction. Wonder is allowed, but it must pay rent in the currency of constraints. Now we name what the standard model does not cover, because these are the cracks where speculation gathers. It does not include quantum gravity, and it does not explain dark matter or dark energy. These are not small omissions, they are entire domains where our best theories stop talking to each other cleanly. When the map has blank regions, people naturally imagine hidden cities, yet the blankness itself is not evidence of what is inside. General relativity describes gravity as space-time geometry, and it works on planets, stars, and galaxies. It predicts the precession of Mercury, the bending of starlight, and the expansion history of the cosmos. It also predicts black holes and gravitational waves, which have moved from theory to observation within living memory. The visual is almost too clean, a smooth fabric of space-time curving under mass and energy. Quantum field theory describes the other forces, and it works in accelerators and materials. It handles the jittering vacuum, the probabilistic outcomes, and the discrete quanta exchanged in interactions. It is the logic behind lasers, MRI machines, and the stability of matter. Putting them together is still unfinished because quantizing spacetime is not like quantizing a field on spacetime. The stage itself becomes part of the cast. This is not a minor technicality, because collapse theories often lean on gravity. If spacetime itself must be quantized, then superpositions of geometry may be real, and their fate could matter for measurement. A superposition is not just a thing in two places, it is a precise mathematical state with phases that can interfere, and gravity might respond to mass distributions in ways we do not yet fully formalize. Penrose's objective reduction sits exactly on that temptation. It proposes that superposed spacetime geometries become unstable, and collapse happens when gravitational self-energy crosses a threshold. The idea is that nature may not tolerate indefinite ambiguity in geometry, because geometry is what defines distance and time. In this picture, collapse is not a psychological event, it is a physical settling of spacetime's bookkeeping. The claim is bold, because it would make collapse a physical process, not just an update of knowledge. It would also make collapse potentially relevant to brains, if biological systems could orchestrate superpositions near that threshold. That "if" is doing heavy work, because brains are noisy, thermal, and chemically active. Still, the allure is obvious. A new law that selects outcomes could seem like a bridge from physics to experience. But the honest status is speculative, and we have to say that clearly. We do not yet have a confirmed quantum theory of gravity, and we do not yet have decisive evidence that gravity causes collapse. Penrose's proposal is a hypothesis in a landscape of hypotheses, not a settled extension of the standard model. The history of physics is full of beautiful ideas that died under better instruments. So the right question becomes experimental, not rhetorical. If objective collapse is real, it should show up in non-biological systems, because physics does not grant brains special exemptions. A collapse law would not wait for neurons to appear in the universe. It would act in crystals, in mirrors, in molecules, anywhere the relevant superpositions exist. The frontier is mesoscopic superposition, where objects are large enough to feel classical, yet small enough to be put into quantum states. Think interferometry with massive molecules, optomechanical resonators, and levitated nanoparticles pushed toward macroscopic coherence. Picture a tiny bead suspended in a trap, isolated from air molecules, cooled toward its motional ground state. The visuals here are stark and almost monastic. Vacuum chambers, laser light, and instruments listening for whispers. These experiments can constrain collapse models by watching interference survive or disappear beyond what decoherence predicts. Interference is not a metaphor. It is a measurable pattern that depends on phase coherence. If interference dies too fast even in extreme isolation, collapse becomes more plausible. If interference persists as isolation improves, collapse models lose room, because ordinary environmental entanglement already explains the loss. To make that comparison, physicists calculate decoherence rates from known couplings. They account for stray photons, residual gas collisions, internal vibrations, and electromagnetic noise. They also test how the rate scales with mass, size, and separation in the superposition. Collapse theories often predict a different scaling, which is exactly what makes them testable rather than mystical. This is where disciplined wonder lives, because it turns metaphysical heat into measurable light. It also clarifies what Orch-OR needs, because Orch-OR depends on a real collapse law, not just decoherence. If collapse is merely apparent, then Orch-OR loses the special event it needs to produce definite moments of experience. If collapse is real, Orch-OR still has to show that biology can reach the relevant regime without being drowned by noise. Now we revisit decoherence, because it is often treated as a final answer when it is not. Decoherence explains why quantum superpositions become effectively classical when entangled with the environment. The key word is effectively, because the full quantum state still exists in the mathematics. What changes is what can interfere and what can be accessed by any local observer. It selects stable pointer states and suppresses interference in practice, turning phase information into inaccessible correlations. The environment becomes a sink that records which path information, even if no one looks. In many models, the environment redundantly encodes information, a process sometimes called quantum Darwinism. In plain language, the world keeps copying certain facts until they become the only facts anyone can reliably see. It explains why cats look either alive or dead, and why macroscopic objects have definite positions. A dust grain in sunlight is constantly bombarded by photons, and each scattering event entangles the grain with the field. The coherence between here and there becomes astronomically hard to maintain, even if the underlying equations never forbid it. Classicality is not fundamental in the equations. It is an emergent stability created by relentless interaction. But decoherence does not, by itself, solve the measurement problem's core. It explains the appearance of outcomes, yet it does not uniquely explain why one outcome is experienced rather than many, or why probability becomes actuality. The formalism gives you a mixture-like state for what you can observe locally. It does not tell you whether the universe truly splits, whether something collapses, or whether the wave function is merely a tool. Interpretations still differ on what the wave function means, and whether collapse is real. Manyworld says all outcomes occur in branching histories, and collapse theories say one outcome is selected by new physics. Epistemic views say the wave function encodes knowledge, not reality, so collapse is just updating information. Each view can reproduce standard predictions, which is why the debate persists even among professionals. This matters for consciousness claims, because some theories quietly swap these meanings mid-sentence. They treat decoherence as if it creates a single outcome, then treat collapse as if it requires a mind, then treat the mind as if it is a field. When definitions slide, the argument feels smooth while the logic breaks underneath. If the story is about physics, the terms have to stay pinned to their operational meanings, so we state the boundary in one line. Decoherence is a physical process we can calculate and measure indirectly, and collapse remains an interpretational or speculative add-on, unless new evidence appears. That boundary is not meant to kill wonder. It is meant to keep wonder from claiming victories it has not earned. Now we shift from physics gaps to brain gaps, because neuroscience also has open problems that invite overreach. The brain is not a solved machine, even if its dependence on biology is undeniable. We can record spikes, image blood flow, and perturb circuits, yet the leap from mechanism to lived experience still resists a single, satisfying translation. The temptation is to import exotic physics, but the first responsibility is to exhaust the power of known neurobiology. First is the binding problem, the question of how distributed features become a unified percept. Colour, motion, shape, and meaning are processed in different circuits, yet experience arrives as one scene. In the visual cortex, different areas specialize and signals travel through multiple pathways with different latencies. Still, you do not see a red patch and a moving edge as separate files. You see a single, moving red object. Some binding is explained by attention, synchrony, recurrent loops, and predictive integration across hierarchies. Neurons can synchronize their firing, and that synchrony can act like a temporary tag that links features. Recurrent processing allows higher areas to send feedback that stabilizes interpretations, especially under ambiguity. Predictive coding frameworks suggest the brain is constantly matching incoming signals to internal models, binding features by explaining them with a single cause. Yet no single mechanism has closed the case, and unity remains hard to localize in a distributed network. If binding is everywhere, then where is the place where it becomes one thing? If binding is nowhere, then why does it feel so singular and immediate? The question is not just technical, it is a clue about what kind of explanation consciousness will ultimately require. Second is temporal unity, the fact that consciousness feels continuous while neural events are discrete and delayed. Signals take time to travel, synapses integrate over milliseconds, and decisions can be biased before we can report them. Yet the subjective present feels like a coherent now, not a staggered cascade. The brain seems to build a present tense out of asynchronous parts. The brain integrates over windows, often tens to hundreds of milliseconds, stitching inputs into stable percepts. Those windows show up in psychophysics, in oscillatory cycles, and in the timing of report and decision. Gamma and alpha rhythms, among others, appear to gate information flow and sampling, though their roles vary by task and region. The stream may be a sequence of overlapping integration frames, smoothed by memory and prediction. Yet the exact mechanism of how moments become a stream remains contested, and different tasks reveal different integration scales. Some perceptions update quickly, while others require longer accumulation. Under stress or novelty, time can feel stretched, suggesting that attention and arousal reshape the window. The question lingers: is the continuity a property of neural dynamics, or a property of how the brain narrates itself? Third is the state control problem, the question of why consciousness turns off so reliably in anesthesia and deep sleep. We can map correlates, yet the causal chain from molecules to network collapse is still being refined. The clinical fact is blunt. A small concentration of a drug can erase experience while leaving many reflexes and computations intact. That selective vulnerability is a constraint as hard as any equation. Anesthesia is the cleanest lever we have because it is reproducible and reversible. It also exposes a key constraint for every theory, because consciousness can vanish while many local computations continue. You can still have sensory processing in early cortex, and you can still have spinal responses, yet the integrated, reportable world disappears. Whatever consciousness is, it depends on more than isolated islands of activity. Leading models emphasize network connectivity and thalamocortical loops. Many anesthetics reduce effective connectivity, weaken long-range feedback, and disrupt the recurrent dynamics associated with global availability. The thalamus is not a seat of consciousness, yet it is a hub that coordinates cortical communication. When those loops lose coherence, information can still exist locally while failing to become globally accessible. Different drugs act through different receptors, yet they converge on similar system-level signatures. GABAergic potentiation increases inhibition and fragments communication. NMDA antagonism disrupts excitation and integration, and neuromodulatory shifts alter cortical gain. In imaging and EEG, you often see reduced complexity and altered oscillatory patterns, especially in frontoparietal networks. The convergence suggests that consciousness depends on a dynamical regime, not a single molecule. Measures like perturbational complexity and related metrics often drop under anesthesia, tracking the loss of rich differentiated dynamics. In some paradigms, researchers perturb the cortex with a pulse and measure how widely and intricately the response propagates. Awake brains tend to respond with complex distributed patterns, while anesthetized brains respond with simpler, more local echoes. These findings fit with frameworks that emphasize integration and broadcast, even if they do not settle the hard problem. Now, we address microtubule-centric anesthesia claims with the same discipline. Orch-OR points to anesthetic binding to hydrophobic pockets in proteins, including tubulin, and suggests this disrupts quantum coherence. The claim is not that microtubules are unimportant. They are essential scaffolds and transport highways inside neurons. The claim is that they are also the site of a delicate quantum computation that anesthesia switches off. The strongest mainstream evidence still supports receptor and network-level mechanisms as primary drivers. Binding to GABA-A receptors, NMDA receptors, and other targets has clear pharmacology, clear dose response, and clear links to neural dynamics. We can mutate receptors and change anesthetic sensitivity, and we can track how synaptic currents shift under drugs. Those are direct levers on excitability and connectivity, and they map cleanly onto loss of responsiveness. Microtubules are essential for cellular structure and transport, and disrupting them can harm neurons. They guide axonal transport, maintain shape, and help organize intracellular traffic over long distances. But essential is not the same as being the seat of consciousness, and anesthesia happens without the catastrophic cytoskeletal failure you would expect from a primary microtubule shutdown. If microtubules were being globally disabled, neurons would not simply wake up minutes later with no structural crisis. So the question becomes narrower and testable. Do anesthetics produce specific, measurable changes in microtubule dynamics that predict loss of consciousness better than network connectivity measures? If microtubules are central, their state should track consciousness across different drugs, doses, and species. It should also track transitions like sleep and coma, not only pharmacological sedation. If microtubule quantum coherence is central, then coherence signatures should change with anesthetic state in lawful ways. Those signatures should survive alternative explanations, and they should be detectable under physiological conditions with independent replication. The burden is not to sound profound, but to specify observables, spectral features, coherence times, or interference-like effects that can be measured without interpretive gymnastics. If the signatures are absent, or if they are present but not causally linked to reportable experience, then microtubules remain important biology, not demonstrated quantum mind hardware. That conclusion would not diminish the brain's mystery. It would simply place the mystery where the evidence points, rather than where the metaphor feels most dramatic. Now we name the most common failure mode across the entire quantum consciousness conversation. It is the category error, confusing metaphorical quantum language with physical quantum mechanisms. People say the mind is a wave, thoughts are entangled, and intention collapses reality. These phrases can express felt unity and uncertainty, yet they often smuggle in claims about Hilbert spaces, coherence, and measurement without specifying observables. In physics, quantum is not a synonym for mysterious. It means superposition with phase, interference patterns that can be predicted, and entanglement verified by statistical tests like Bell inequalities. Entanglement is not everything is connected in a vague spiritual sense. It is a precise correlation structure that violates classical bounds under controlled measurement settings. If you cannot say what inequality is being tested, you are not describing entanglement in the physicist's meaning. A metaphor can be meaningful, yet it cannot substitute for a mechanism. If a claim cannot tell us what to measure, what to vary, and what result would falsify it, it is not physics. Mechanisms live in the details: timescales, coupling strengths, noise sources, and amplification pathways. Without those, quantum becomes a costume that mystery wears to look legitimate. We also correct a subtler category error that hides inside respectable language. Observer in quantum experiments can mean any irreversible record, not a conscious witness. A photodiode, a bubble chamber track, or a stored bit in memory can serve as an observer in the operational sense. The key is that information becomes effectively irreversible because it is dispersed into many degrees of freedom. This does not prove consciousness is irrelevant to measurement, but it blocks an easy shortcut. If consciousness is required, the theory must explain why unconscious detectors still behave as if outcomes occur. It must also explain why the statistics of outcomes match quantum predictions regardless of who is watching. The universe does not seem to wait for awareness before it keeps its accounts. Now we pull the threads together because this is the climax where the map must become a stance. Physics has a standard model that predicts astonishingly well, and it does not mention consciousness as a causal variable. It gives us fields, symmetries, and interactions, and it never once needs a mind term to predict a spectrum or a cross-section. That silence is not a refutation of experience, but it is a constraint on how experience can enter the story. Physics also has open problems, and those problems are real, not rhetorical. Quantum gravity is unfinished. Dark matter and dark energy remain unidentified, and the measurement problem remains unsettled at the interpretational level. The gaps are genuine, and they are among the deepest questions in science. Yet a gap is not a doorway with a sign that reads "consciousness goes here." Neuroscience has powerful constraints, and it also has open questions. Binding and temporal unity are not fully explained, and state transitions like anesthesia and sleep still hide mechanistic details. We can name candidate circuits, rhythms, and computational principles, yet the full account is still under construction. The brain is a physical system, but it is also a system that generates a world from within. Here is the temptation, and we say it out loud. When physics has gaps, and neuroscience has gaps, consciousness theories try to move into the gaps, because gaps feel like permission. The move is psychologically understandable, because consciousness feels like the most intimate mystery we have. But intimacy is not evidence, and mystery is not a measurement. But mystery is not a license, because gaps close in unpredictable ways. Many historical gaps were filled by ordinary mechanisms that were invisible, until instruments improved, and the universe did not reward our preferred metaphors. Life once seemed to require a special vital force, until chemistry and biology made that force unnecessary. The lesson is not cynicism, it is humility about how often the world chooses the unromantic answer. Still, mystery is an invitation, because gaps also mark where new physics could enter. Objective collapse might be real, and quantum biology might reveal new coherence niches, and neuroscience might find deeper principles of integration. The invitation is conditional. New ideas must connect to old successes without breaking them. The deeper the claim, the more it must respect what is already known. So we define what responsible speculation looks like in this documentary. It respects established models, it names open problems without inflating them, and it makes predictions that could fail. Responsible speculation is not timid, but it is disciplined. It does not hide in ambiguity when the data arrives. A responsible quantum consciousness claim must specify a substrate, a timescale, and an amplification pathway into neural computation. It must show why coherence survives long enough to matter, and why classical explanations cannot reproduce the same signatures. It must also show how a microscopic quantum event becomes a macroscopic change in firing, behavior, and report. Without amplification, even a real quantum effect can remain irrelevant to cognition. A responsible collapse-based claim must connect to non-biological tests, because physics must be universal. If collapse cannot be detected in controlled mesoscopic experiments, then brain-specific collapse becomes special pleading. The brain can be special in its organization, but it cannot be exempt from the laws that govern everything else. The same collapse parameter that applies to a nanoparticle must apply to a neuron. A responsible neuroscience claim must explain why unity feels singular when mechanisms are distributed. It must connect binding and temporal integration to known anatomy, known rhythms and known pharmacology, not just to a poetic sense of wholeness. It must also account for why consciousness scales with certain kinds of connectivity, and why it fails under specific disruptions. Theories that cannot survive anesthesia are not theories of consciousness in the world we live in. Now we return to the viewer's inner life, because the series began there and it must not be abandoned. Your experience is the most certain fact you have, and it is also the hardest fact to place inside equations. You can doubt a measurement, a memory, even a worldview, yet you cannot doubt that something is happening right now, because the doubt itself is part of the happening. Today we can responsibly conclude two things at once, without forcing a false choice. Consciousness is tightly linked to brain dynamics, and altering those dynamics alters experience with clinical reliability. Injure a network, change a neurotransmitter balance, or interrupt long-range feedback, and the contents of experience change. That link is not a philosophical preference. It is a medical and experimental reality. We can also conclude that claims of a quantum or cosmic source remain speculative, because the decisive evidence is not yet in hand. The wonder remains, but it must be held inside boundaries that keep it honest. If quantum effects matter, they will show up as specific signatures under controlled conditions. If they do not, the mystery of consciousness remains profound, but it remains a mystery of brains and computation rather than a loophole in physics. The final step is not to close the mystery, but to sharpen it. If the universe is connected to mind, the connection will leave traces that experiments can find. What would those traces look like, and where would they hide from our current instruments? Would they appear in mesoscopic interference, in anomalous decoherence rates, or in neural dynamics that defy classical modeling? Next chapter, we stop expanding the map and we choose a position that fits the constraints. We keep the hook alive, but we let the evidence decide how far it can reach. We pull back from microtubules and metaphysics to the strongest constraint. consciousness tracks brain state with clinical reliability through sleep, lesions, and anesthesia, an everyday fact in neurology wards and operating rooms. On screen, EEG rhythms slow and simplify, then bloom into complexity as a patient wakes. Classical neuroscience explains mechanisms and correlates, from thalamocortical loops to neuromodulators that gate arousal, yet the hard problem still bites. Quantum mechanics explains matter's substrate, where superposition and entanglement shape the microscopic rules. But linking that formalism to experience is non-trivial. Orch-OR offers a compelling narrative, with microtubules as organized scaffolds inside neurons, yet decoherence, testability, and quantum gravity assumptions remain major hurdles. Historically, physics has humbled intuition before, but it has also demanded measurements that survive hostile replication. Minds would change with risky predictions like coherence signatures tied to report, anesthesia to tubulin causality, and mesoscopic collapse constraints that rule out convenient wiggle room. A disciplined middle view holds that quantum effects pervade matter, yet quantum is not automatically experience's missing ingredient. From a cosmic perspective, observers are physical systems within the universe, not outside it. We are atoms that learn to model atoms, staring into deep time while our own neural states flicker. Mystery becomes a research program, bounded by falsifiability and humility. The universe may not need consciousness, yet consciousness is its intimate self-knowledge. We began inside the private interior universe of experience and followed its shadows through split brains, sleep, seizures, and anesthesia, where consciousness fades with brutal clinical reliability. Along the way, neuroscience showed us powerful mechanisms: spikes, synapses, neuromodulators, and long-range recurrent networks, while admitting that decoding activity still does not explain why anything is felt. Then, quantum theory entered, not as poetry, but as the strangest successful math we have, with superposition, entanglement, and decoherence drawing a hard line between what is permitted and what is merely suggested. Microtubules and Orch-OR offered a detailed bridge, proposing protected coherence and objective collapse as discrete moments of awareness, yet every step demanded numbers, timescales, and coupling paths that the warm, wet brain may not grant. Beyond Orch-OR, we tested other quantum mind routes, separating quantum probability models that explain decisions from claims of literal coherence, and asking the same question each time. Where is the Hilbert space? Where is the interference? And where is the risky prediction? At the cosmic scale, we confronted panpsychism, cosmopsychism, and information-first stories, and found that metaphysical elegance is not the same thing as laboratory confirmation. The through line never changed. Whatever consciousness is, it opens and closes with brain organization, and any deeper physics must honor that boundary rather than evade it. So we end with a disciplined middle view. Quantum rules underwrite the matter we are made of, but quantum language alone does not yet buy us an explanation of experience. If there is an extra ingredient beyond classical emergence, it must show itself where science can corner it, in measurable coherence signatures, anesthesia-linked tubulin causality, or collapse laws that first reveal themselves in non-biological mesoscopic tests. Until then, the hard problem remains a real problem, not a license to smuggle answers in through the word quantum. So is your brain a quantum antenna, and are your thoughts entangled with everything that exists in a way that makes consciousness cosmic? What we can say, with confidence, is more sobering and more beautiful. The brain is not closed in a physical sense, yet the evidence still points to consciousness as a local phenomenon of organized biology, with quantum cosmic extensions remaining speculative until they earn their signatures. Entanglement gives correlations without messages, decoherence makes fragile phases vanish fast, and the universe does not hand us privacy violations just because the math feels uncanny. The opening question survives, but it changes shape. Less are we connected, and more. What kind of connection would leave a trace that cannot be explained any other way? Perhaps the deepest lesson is that mystery is not a gap to fill with metaphors, it is a set of constraints that forces our best ideas to become testable. Consciousness may be the most intimate fact we know, and the least well placed in our equations, yet the search for its bridge is how we learn what a mind is, and what a universe can be. If you want to follow the next step of this story, look for the risky experiments, the hostile replications, and the precise predictions, because wonder becomes knowledge only when it can be wrong.